This morning, I would like to share with you about TC Seroja, one of the systems that developed in our responsibility area in April 2021. So, TC Seroja infest was first detected in 2 April 2021 in Sulawesi. It's a water area in East Nusa Tenggara province in Indonesia. And during its life period, it has caused significant impact on the weather, especially for this region. We have recorded the extreme daily rainfall up to 332 millimeter in Kupang City in NTT region at 4 April 2021. And we also recorded a strong surface wind speed of 52 knots, also in the same met station in Kupang at 4 April 2021. So it is still on its initial stage of development. And based on the data that we have from National Board of Disaster Management of Indonesia, the BNPB, it is reported that this system has caused 183 people die because of it, and then 47 people missing, 184 people injured, and more than 84,000 people have to evacuate it from their house. And the total loss in economic by this tropical cyclone was estimated around 255 million US dollars. So this is the trajectory from the tropical cyclone Seroja. So as you can see, this is the track for period 2 until 6 April 2021. This is the initial stage of development. As you can see, this system is propagate in circular motion in East Nusa Tenggara province, and it remains for approximately 3 or 4 days in our region. So that is why the impact on the hazard is quite significant for this region, the Nusa Tenggara Timur region. And then after it reached the intensity of tropical cyclone, it started to have a more stable propagation into the southwest of Indonesia and moving away from our region. So you can see on the complete track of TC Seroja here, after it becoming the tropical cyclone, it moves along the southwest propagation and then shifting to the southeast and entering the western part of Australia before it weakened it and then decaying on 12 April 2021. So actually, beside the TC Seroja, we already have another several TC that developed in our eastern part of Indonesia region. So we have the TC Boni on April 22, and then TC Inigo in March 2003, TC Kirili in April 29, and then TC Errol on April 2011, and TC Jillian on March 2014. All of the system also developed very near on our NTT region. So what we do to analyze the intensity of tropical cyclone that develop in our responsibility area? So mostly we use the satellite imageries. We have the Himawari 8 satellite imageries, and then we have a platform called SAT-AT, where in this platform we conduct the diffract analysis. And this is the example what we do for the TC Seroja infest, the 99S. We make a diffract analysis using the SAT-AT to define the center of the system and then the intensity and also the T number and finally the current intensity of the system at that moment. And beside this method, we also use the spectrometer and so the water vapor and other satellite derived products. So this is the diffract analysis for 4 April 2021 at 12 UTC. At that moment, the 99S, we can see that the curve band pattern is quite clear at that time, and we can start to make the diffract analysis using this pattern. Well, as I mentioned before, that the 99S, the infest from the TC Seroja, declared as the infest at 2 April 2021, but actually the system is already developed at 30 March 2021 at 0 UTC in Bandasi. So this is in the northeast of NTT region in the form of eddy circulation. And then in the next 48 days, it moves southwest to the Timor Sea and already become a low pressure area intensity. And then in the next 24 hours, into April 2021, it moves to the South Sea, and it's still in the form of low pressure area, and then we declare it become the infest of tropical cyclone. And the background condition of the atmosphere at that time, but we have the MGO active in our in the entity region on its phase 4, and then we also have the equatorial Rossby and also the Kelvin waves. And also at 2 April 2021, as you can see in this chart, beside the 99S, the infest of tropical cyclones Roja, we also have two another infest in our area. So we have the 90S also in our responsibility area and 90B in Northern Indian Ocean, which is our monitoring area. So we have 3 systems at that time. Yeah, so, excuse me. So after we declare the 99S become the infest, we make the genesis of the system. So at 2 April, we find that in the system, the maximum wind is still 25 knots, and the circulation is there, detected in all of the level, but still weak and elongated. And then we do still have the moderate vertical wind shear. And then after that, in the day after, the system become more well-formed, and then the maximum wind also increasing into 30 knots. And the vertical shear also become more favorable because it's decreasing between 10 until 15 knots. And after that, on 4 April 2021, the system become stronger because we find the area with the maximum wind 30 knots become more visible on the system, and also the circulation still well formed, and the vorticity in the level also becomes stronger than the day before. And we also have the MGO now active in our phase 5, which normally is enhance the convection in our eastern part of Indonesia. So that was where the system is situated. Yeah, this is the complete cyclogenesis of disease Roja, as I mentioned before. So at 4 April at 18 UTC, the system is born into the tropical cyclone Roja with a maximum wind at 35 knots and 1994 millibar. And then it leaves our monitoring area and entering it leaves our responsibility area and then entering the area of TCWC Perth, Australia, and then it's getting stronger into category 3 with the maximum intensity is 70 knots and 9,078 hectopascal. So what do we do in forecasting the track and intensity for the cyclone in our region? So this is the flow chart that we do in the operational. So we do have the NWP models output. We have forecasting tools named Synergy. In Synergy, we visualize the output from these different NWP models. And then normally we will choose, in minimum is 3 models from these several models. And then we will try to locate the LLCC position, and then we try to analyze the surface and the upper level wind, the density level, the humidity, the vorticity, the rainfall, and other parameters that needed. And we also will download the ensemble forecast track from GTWC. And then from these two, the ensemble forecast track and the track that we have from our NWP models, we will combine these two tracks, and then we will make the consensus track using our TC model. And then after being expertized by the forecaster, this consensus track will become our official forecasting track of tropical cyclone. So this is the example that I want to show you about the TC Roja. So this is the forecasting track that we made in 4 April 2021 at 18 UTC. So this is when the system has first reached the intensity of tropical cyclone. The red line is represent the forecast track, and the black line is the analysis track. So as you can see, this is the forecast for 72 hours ahead. So maybe you can see on the screen that in the first 24 hours, the forecast and the analysis track seems in accordance. So the forecast is quite good. But after that, we can see that after 24 hours to 48 hours, we can see that there's a shift between these two lines. Firstly, the forecast become a little more south than the analysis one. And then after, it become a little more shifting to the north than the actual analysis track. And beside that, we can also see that the intensity, there's a quite difference between those two. because in the forecast, it said that in the next 72 hours, the TC Seroja will reach the category 3, while in the analysis track, actually it's still in the first category. So there's different in the intensity also. And also we can see that the movement in the forecast track is faster than the actual analysis track. So it means that the model seems to forecast the movement of the system is too fast than the actual speed of the system. So now we will talk about the hazard from the system Seroja. So this is the impact on the rainfall. You can focus on the red boxes. You can see that this is the distribution of the daily rainfall in Indonesia region. So this is for 30 March, 1 April, 2, 3, 4, and 5 April. So this is the period when the TC Seroja developed and also active in our region. So you can see that even on its initial stage, it's already caused significant rainfall in our region. As you can see, this is the legend. So for the red one is the heavy rainfall, and for the purple or all the red is an extreme rainfall. Yeah, so you can see that the rainfall is already there on 30 March when the system is still in abundance in the form of eddy circulation, and then it become more significant, and you can see an extreme rainfall already occur at 2 April 2021 until 4 April 2021. So the system not even reached the intensity of tropical cyclone, but the impact is already very massive. And we can see that the precipitation also shifting to the southwest along with the system that also move in the southwest direction. And this is the hazard for the wind speed. So normally in East Nusa Tenggara at this month, the wind speed maybe is only about 10 until 12 knots. But when we have the TC Seroja develop in our region, as you can see, we have increasing of wind speed in 6 met station in our region, in East Nusa Tenggara region. So you can see that from the 1st April, we have enhancement in wind speed in most of the met station, and then it becomes stronger when the system intensify, and we can see that the peak is happened at 4 April with 52 knots, and it's still very significant even on the next day on 5 April. So we have mostly up to 20 knots surface wind speed on all of the met station in Nusa Tenggara region. The same hazard also can we see on the sea waves. So you can see that the yellow shade is a moderate sea, and then the orange is rough, the red very rough, and purple is extreme with sea waves with a height more than 6 meters. So you can see this is the area where the TC Seroja is developed. So we can see that the impact on the sea waves is very significant. The extreme sea waves, we can find it in the South Indian Ocean, in the southern part of NTT region, and also in South Sea and south of Timor Sea. This is the analysis one, so not the forecast. And because of all of those hazards, of course, it will trigger the hydrometeorological disaster. So this is the data that we gather from the mass media for the period between 1 April until 10 April 2021 for 4 different phenomena: the weak tornado, the strong wind, flood, and also landslide. So you can see in this 10 days period, this is during the tropical cyclone Seroja period, you can see that this 4 parameter is happening in Nusa Tenggara Timur region. And the highest frequency of this disaster, we can see it on the 3 and 4 April 2021 is when the system is still on its initial stage. And the most significant disaster was flood, as you can see in a gray bar here. And the second highest was the strong wind. Yeah, so in total, in 10 days period, we have 95 events of hydrometeorological disaster in Nusa Tenggara Timur region caused by TC Seroja. So this is the coordination that we made and also some products that we issued during this period. So actually, after we made the genesis, the Center of Public Weather Services issued the press release regarding the infest of Thesis Roja, the 99S, and then we informed the stakeholder and also our representative office in NTT to disseminate the information to their local user. And when the system will intensify into tropical cyclone, our director of BMKG, she invite the stakeholders and the local governments and then mass media to inform this early warning, so they can act to minimize the impact. And we also make the infographical product here. So we made it every 6 hours and then we disseminate on our social media channels. So we can hope that public will aware about this system. And we also make this impact-based forecast product that talk about the hazard of heavy rainfall that might trigger the flood and also the flash flood in NTT region since 1st April 2021. So, yeah. Okay, okay. I think that's the end of my presentation. Thank you very much for your kind attention.
Thank you, Kiki. And to follow that, we have Agi Wandala from BMKG to follow that up with looking at impact-based forecasting. Thank you, Agi.
Thank you, Joe. Good morning. Selamat pagi. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for the opportunity. So I would like to follow up what just Kiki presented, our experience in the implementing of the impact-based forecast, because if we have a look on what we have done in 2021 in April, our early warning is also bound by the impact-based forecast that already served to the public. So this is our experience. But before moving to that part, I would like to also give you some outline that I will start with the story of the shifting paradigms that we just start, because the shifting paradigm process is not just only for the people, but it's also very tough to change the mind of the forecaster, the change of the mind of organizations, because not just only med services, but there's also disaster managers, and also the step-by-step implementations of the IBF and what we got from the Soroja itself, and also including the future, that maybe we just deliver the questions. This IBF is the best approach that we will do, or this is just the concept as usual. So to all of you, or one of you that not really know about what is actually the IBF, so it's really simple presentations that you can understand. So the idea is really basic, because we just shifting the process from the what weather will be into what weather will do. So we take also the same idea into the tropical cyclone approach. The same questions is also that what the tropical cyclone will be into what tropical cyclone will do. Because so many times, or we already had a long times discussing, developing the system that normally we are the physics, the dynamical things that we already delivered, but also we need to think also that people need to really receive the early warning. It's really in line with what just UN said, that early warning for everyone. But from what we just study in Indonesia case, that we think that we already delivered the good warnings, but still, yeah, so many people affected, but even so many people also still not get the main early warnings. To do that approach, Indonesia, starting with the basis of the user needs. This user need is the main approach that BMKG developed, and then we just start slowly moving the impact-based forecast approach, and then moving the risk-based informations. Because at the end, this risk information is the key to give the people start to understand how they not just receive, but they can also respond the informations. So the process of this transforming is actually a long way process. So we start since WMO gave the guideline in 2015 with the 1154 document. We start to analyze and study direct from the document, but also we work together with the NOAA and also UKMO Slowly we start from 2016 and 17, develop the main concept, and then we briefly to start developing the impact metrics and also response metrics in 2018. So to accompany this concept, we also develop our own system, the web services platform to deliver the warnings. We call the signature.bmkg. And then in 2019, finally we got the first services into the public. Of course, it's not ideal one, but step by step we develop the system, and it also start to also known by nationwide. You will see from this slide that basically we need to get step by step from phase 1 to phase 6, from the collecting the data for the hazard and also the response itself. We need to also know the stakeholder that we approaching, and then we need the disaster manager also to involve with, and we need to also have the SOP with and also the interface. So that's what we have done. So basically the system or this concept need to be accompanied by three main components. So the risk information cannot be produced without the component of the hazard, vulnerability, and exposure. So hazard, we not discuss about that. We're talking about the capacity that we also have done in forum with the IWTC, how we can deliver a really good forecasting capacity in terms of the tropical cyclone. But the other side, sometimes we also not really get the real data from the exposure and also the vulnerability. Glad in Indonesia, the disaster manager also have really quite complete data for the exposure in the national wide. Some province is not quite complete, but with those data, we start combining and develop the algorithm to define. So that's why yesterday when we had discussions about the AI, I just proposed that maybe this AI on TC also can expand it into the risk communication, especially on the risk warning on the IBF. So of course, we cannot do by ourselves. We are meteorologists, but we need someone outside our community also need to respond, also need to take an actions, because community is so wide, so big part of the part of the cycle of early warnings. So in Indonesia, we have the BMKG as the meteorological agency, but also we have another entities like the disaster managers, but also we involve the voluntary basis. We also involve the police agency like the army and also the search and rescue and also the national police. So this is important because if we are the one who sit in the national capacity, maybe in the province level, they will not respond. But we need someone in the level of the province and even below, the really lower administrations level, like the head of the community, head of the government, of the local government. So they are the one who hurt by the people. So this is the way. This transforming is not easy. So that's why we do the step-by-step approach and start to give informations, but ensure who need to respond to informations. So basically, it's really simple on the when we deliver, because we need to make a really standard and simply information so people can understand. So from the weather, from the tropical cyclone we'll do, as usual, we're talking about tracking and all the information, intensity, structure, but then we need also transforming into what the tropical cyclone will do. It's containing the area, of course, because we need to see on the geographical aspect who will be affected from the cyclone. And also we need to also think about the level of the risk. So this risk communication is quite important. We combine and also deliver together with the impact informations, the potential impact. And also the one thing who really important is delivered with also suggestions and the recommendations what they need to do. So maybe this one is going to be a big discussions because in each area it will be much different. So let's have a look on the Seroja cases. So as Kiki said that Indonesia, maybe we didn't have many cyclone which is direct impacted to Indonesia, but the indirect impact is so many. And also from the Seroja events, we can also understand that the initial state is really important. We can see that this initial state is also already give the hydrometeorological impact in the nations, in the some area. So from the story of the Seroja, I just show you the previous versions of the impact base. So we just give just before its form. So just before the initial stage, we already start to communicate with the local government. We start deliver the informations of the risk base warning. So maybe it's quite different when we're talking about the track and really big map of warnings, but then we really specify until lower administrations level. So before we already give the orange alert, which is already high until the level 8 and 9, which is the be prepared in some area. So from this information that we can see that they are already warned by governments or by the formal institutions, but then the recommendation is become questions because we don't know that they take this response or not. Because finally, from what just presented before, the data is still so many casualties impacted due to the Soroja events. So I want to also to show you that this early stage capacity on the detections of cyclone is really important because like Indonesia, we really need this information. So the consistency of information is already beginning just before the initial state is just founded. So from, if I said 31st March, it's going to be 3 days before we already detected this activity. So step by step, we inform the people close to the day just before the cyclone already formed on the stage. So the consistency of the warning is already delivered. But then the question is again, how many people that already informed, and also what they can do after they receive the information. So this is the challenge that everywhere, I think, not just for Indonesia. The other side also, we can see that, of course, we're focusing on the capacity. The story of Soroja, that we have the radar, already observed the area of Nusa Tenggara. But then we also discussing about the capacity of the local observations. That's the things that we discuss a lot, the validations data, how we can get the informations, but then also we can also imply with the capacity of the warnings that we delivered. So from the slide that before and also during the cyclone, we combine between the analysis of the cyclone itself and also how we can still inform the public, because that's messy, that's people confused, because most of them is, even they stay in the really prone area of cyclone, but they still don't know what kind of these activities. So that's shown on the survey after this that my colleagues will explain. So we can learn that during the Soroja events, that this IBF approach is really useful because we can start talking about the situation just before the analysis of the Soroja itself, and then just the Soroja form. And we can also start to communicate to the public, to the people who really affected, the potentially affected by cyclone itself. But then we're talking about the heavy rainfall right now. Heavy rainfall impacted on the flooding, landslide, flash flood, and all aspects of rainfall. But the other side, the wind impact still not main focus at that time. But for the wave, of course, it will be accompanied. So I was thinking that in the future we need to develop more and more about this, the wind impact. And also, again, we can say that we are really sorry that still so many casualty, but we can say that some community already informed. So I think this is the part that we can give to the people so they can prepare as early as they can. So that's the mean of the early warnings. So one a good example, this guy, Mr. Dewa, Pak Dewa, is the leaders of some community in the East Nusa Tenggara. So glad that he already passed a public outreach programs. It's called the Fishery Field School, the program for the weather applications that can use by the people in the community. And he already know that in the several days, something will be happen in East Nusa Tenggara. So he just informed his community, and they start to make surviving plan, and glad his community is safe. So we glad this, in the future, we want to more and more make new Mr. Dewa to the other area, to the other community, because this guy has give good example that they can give a lot of influence to save the people. Well, to close my presentations, that we will see that from the survey that will deliver letters, that I just want to underline that still so many people not really know about the cyclone. Still so many people feel that they didn't receive. But if they receive the information, they also not really understand what they need to do. So again, this impact-based forecast is really important to moving forward and become main platform on the multi-hazard early warning system in the future. So I was thinking that some capacity need to be expanded related with the coordinations, related with the awareness and also educations to the public. That's really important. But the other side, for our community, we'd also need to focus on the increasing capacity on forecasting of TC on early stage. So because this is the one that mostly in our area experiences. So thank you very much. Selamat pagi.
Thank you, Dr. Agi. And I think that is a perfect lead into our morning session today. But we do also have one last one from BMKG about Seroja, looking at the post-impact survey. So I welcome, and I should just add for everyone online as well. So these presentations are available as PDFs right now. So if you want to follow on your devices, you can also follow the PDFs that's linked from the IWTC webpage. So it's my pleasure to introduce now Idan Abu Bakar. So please, I will show you. Please welcome Idan.
Okay, thank you very much for the opportunity. First, allow me to introduce myself. My name is Idan Abu Bakar from TCWC Jakarta BMKG. And for this opportunity, I will presentation about post-cyclone public survey in the tropical cyclone Seroja cases in the East Nusa Tenggara province. Okay, and this is my outline. The first one is the season cyclone 2020 and 2021, and also 2021 and 2022 TCWC Jakarta. And the second one is the post-cyclone public survey and the result of the survey, and for the conclusion, including the best practice, lesson learned, and also challenges. On the cyclone season on 2021-2022, we experienced one tropical cyclone developed in our responsibility of TCWC Jakarta, and we name it TC Teratai. On the top left, you see the location of the system is the southwest of Java, and the and the bottom one, on the left one, this is the product that our produce, and we give this we broadcast this information, including the track and also the impact to our website, our social media, and also to the local government. We also send this information to our local station, so they can make communication to the local government. So the local government can make like a plan or like what they have to do, including the what they must supposed to do then. And in the top right, in the satellite imagery, when the TC Teratai occur, the pre-development stage 92S start occur on the November 30, 2021, and it become tropical cyclone Teratai on the 1st December 2021, until become extinct on the 2nd December 2021. Some areas such as the western part of Java and also the southern part of Sumatra experiencing the heavy rain accompanied by the strong wind with the short duration. And the picture in the right bottom is the daily precipitation accumulation on the 2nd December 2021 from the GS map. It shows some area in the southern part of Sumatra reach more than 100 millimeters per day, but there is no big casualties there is no big casualties reported so far. So in general, the impact of tropical cyclone Terata in Indonesia are not very significant. In the season cyclone 2020-21, just like Ms. Kiki already mentioned, they already mentioned about the analysis, the intensity. We experienced one tropical cyclone in the 4th April 2021, and we call it TC Seroja. This system occurred at Sulawesi at Nusa Tenggara province, and this is the first tropical cyclone across the land since the establishment of the TCWC Jakarta on 2008. And in the TCC meeting, it has been decided to retire the name of Seroja and change the name into the TC Rambutan. Based on document TCP24 on the chapter 6, end of season procedure point 6.4 about the cyclone damage assessment report and post-cyclone public survey. And this year we finally have a chance to do this public post-cyclone public survey about this tropical cyclone. And the picture at the bottom is the map of East Nusa Tenggara province. Unfortunately, because the East Nusa Tenggara province consists of so many islands, so it's hard for us to invite every single island. So we only visiting 2 islands to take a sample and interviewing them, which is the Timur Island and also the Rotendao Island. The red dot in the picture shown the sampling of distribution area. Survey was held in the 5 of 7 regencies on both island and spread in the 13 districts. The respondents are the public and stakeholder. And this on the top of the picture at the top is when we interviewing the community on the people in the area. And this is the survey result. Before the tropical cyclone Seroja, almost 80% people in the East Nusa Tenggara have no knowledge about tropical cyclone and their impact. That's why the awareness before this event is very low. More than 50% didn't receive the information about the tropical cyclone, both before and the time of their occurrence. Most of them know about the Seroja after the event. And in this diagram, we can see almost 70% says our information still didn't fulfill their needs, especially for those people who live in the rural area. Because a few days before the system become tropical cyclone, they already experienced the heavy rain accompanied with the strong wind. So because the lack of the public facility in those rural area, the electricity was shut down, and also the communication network is already shut down. So even though they already have like initial information, they cannot get the updated one. And in the second diagram, we can see the 100% says they need the tropical cyclone information, include the preparedness action. So that's why we have to strengthen our coordination with the local government and educate them so they can make a better mitigation plan if something like this happen again in the future. Just like Mr. Agi presentation, we already have like a program that we educate the people. For the example, like the fishermen, that we get them so they can have a better experience and they know what they do when something like this happen in the future. Our product information about early warning of tropical cyclone is still difficult for the public to understand. You can see here more than 40% says it's difficult. We already make infographic like a picture that I shown on my presentation, or you can see on Ms. Kiki presentation. we already make like infographic, and I think it's easy to see. You can see the map, you can see the track. We already write the impact of the system, but um, I think still most of them still didn't understand about it. Especially for the example, like for the elder, uh, it's hard for them to understand because some people in the, especially in the rural area, they don't even know a national language. They only using the local language. Or in the other people, it's hard for them to understand a very technical word like a tropical cyclone. They don't know about what is tropical cyclone is and what the impact, because as I mentioned before, this is the first cyclone across the island. So this is our first experience. So for the solution, I think we have to make another product and simplify the information, or maybe make the information in the local language, just for example. And that's why on diagram on that side, most of them side the quality of our information is still poor. This is for the best practice. Coordination between the stakeholder, BMKG, local government, National Disaster Management Agency, and other related institutions has been well established. But we still have to educate them regularly about how to read our information, and more discussion about preparation and mitigation plan. And village headman or a chief of the village, especially who live in the rural area, has an important role in the process of the disaster risk reduction as a liaison between the local government and the community. There is one village that was a best practice. The name of the village is Papela on the Rote Island. Most of the population in that village work as a fisherman. The chief of the village also was a fisherman, and he always update with the weather information from BMKG, and also have a good coordination with the local government and risk disaster management agency. So few days before, he already get the information about the low pressure occur and move toward to their area. And they already informing to all fishermen in their area to not go to the ocean to catch the fish. And wait the information from the, the government. And when they already get the information, the system already moving to their area, so they ask for help to the risk disaster management agency and local government to evacuate their people from their houses. So in the result, so many houses swept away by the wind and the heavy rain, but at least everyone's safe. So we can conclude well-informed community and well-coordinated evacuation process are the key in the event of disaster such as tropical cyclone. And the picture of the right corner is the man who used a red shirt with the strip white and black. Is the chief of the village, and the picture, the rest of the picture here is when we interview them. So this is the video when the evacuation process at Papela village before the tropical cyclone Seroja across the island. Yeah, so the chief already informed the risk disaster management and also the local government before the system across their area. Okay, for the lesson learned, I think the clear preparedness action statement are important, especially regarding when and where to evacuate, and whether socialization in the rural area is very important. Fishermen are more understanding and more active in the seeking weather information. Infographic with a simple message is more acceptable to the public. Online and offline product are needed because in the rural area, when the communication network lost or already disconnected, they didn't get the information. And BMKG is still the most trusted source of weather information by the public. And last one is after the Seroja event, public awareness about the weather information rose rapidly in its use in everyday life. And the last one for the challenges. Before the tropical cyclone Seroja, most people at Nusa Tenggara Timur were unfamiliar with the tropical cyclone and their impact. From the survey, many people still have not received information about the tropical cyclone both before at the time of their occurrence. They already know Seroja after the event. Actually, most of them already get the information because we broadcast our system on the like a Twitter, Instagram, and etc. They already get the information because this is might be the first experience. They simply just totally ignore the information. So early warnings of tropical cyclone is still difficult for the public to understand, as I mentioned before, because maybe our information contain a very technical word. So I think it's hard for the common people to understand about those kind of information. And the problem of power failure and disconnection of the communication network is one of the big obstacles for the community. And also there are still many incidents where the early warning products stop being distributed in the WhatsApp group and are not passed to the public. So when we make a survey, we interviewing the risk disaster management then. So they already have like a WhatsApp group. So every chief village in East Nusa Tenggara province, they have like a one group WhatsApp. And after we give our information to the risk disaster management, they already send and broadcast in the WhatsApp group to inform the people on the field, because the one who can reach the people in the every single region is the chief of the village. But maybe because of the disconnection or low of awareness, maybe some of chief of the village didn't send or didn't inform to their community. So I think that's all my presentation. Thank you for your attention.
Thank you, Idan, and thank you to all our BMKG presenters. We are unable to take questions from the floor or online, but please, for those of you in the room, you can talk directly afterwards, and online we welcome your questions and we'll address them in the chat. I think BMKG's example or their work at the incredible efforts to try and overcome these challenges is a real model for everyone, but that it's sobering to think of the survey results of still how poor the perception is. So very impressed with the efforts, but the challenge is very significant, especially with these unusual events. So we're going now to move to topic 5. So continuing on from that BMKG context, we're going to explore the range of hazards, and it's my pleasure to welcome Monica Sharma here. And I acknowledge we have Robbie Berg as well as the topic leads, and they will introduce the rainfall, wind, storm surge, and tornadoes as well. So I'm going to pass over to Monica to introduce the topic.
Thank you, Chair. So I'm Monica Sharma. I'm Monica Sharma from RSMC New Delhi. So myself and my co-lead, Mr. Robbie Berg from NOAA USA, And along with our team of reporters, will be presenting before you the current status, gap areas, challenges, and recommendations thereof with respect to topic 5, forecasting TC hazards and its impacts. So I request my co-lead Robbie Berg to carry on the discussion further.
Okay, thanks, Monica, and hi, everybody. Wish I could be there with everybody this week for the conference. Had some last-minute snafus with passports, and so unfortunately, my plans changed at the very end. But really glad to at least be able to speak with everybody. And so, want to again.
Excuse me, Robbie. Can you just speak up as loud as you can? It's a bit coming through a bit quiet.
Sure, I will try and speak as loud as I can. So I want to thank Monica for being one of the co-chairs on this group, and then all the rapporteurs there that you see on the screen. This is a very heavy topic-laden or material-laden topic, 4 different hazards, all which deserve their own amount of time. And so we found it a little hard to try and fit everything into the report and then here in the workshop. But I think we did a pretty good job of showing the current state of the science of all these hazards. But what I wanted to quickly start off with before we get into each of the hazards was to kind of just rehash and show you that many of you have seen this before. This is a study that was done by a previous deputy director of the National Hurricane Center, Ed Rappaport, who took a look at all the deaths that have occurred in US tropical cyclones from 1963 to 2012. And I think one of the things that we always point out, and I'm sure this occurs all around the world, is that even though so many people focus on wind, it's the water in the form of storm surge, rainfall, rip currents, offshore incidents. It's those water events that cause the predominant amount of deaths in tropical cyclones. In fact, 9 out of 10 deaths come from the water hazards. Now, that doesn't mean that wind isn't important as well, because wind obviously helps to cause some of these hazards, but it is that water hazard that is most important. Rain and freshwater flooding accounts for almost the deaths in almost half of all TCs in the United States. But I think what's important, I want everyone to keep in mind through this session, is that each of these TC hazards rarely occurs by itself. Usually it's a combination of hazards. And so how do we model, forecast, and simulate the tropical cyclone experience as a whole for the people that depend on our forecasts? Oftentimes we put out a forecast for rain, a forecast for storm surge, for the wind, for the tornadoes, and then we expect people to synthesize all those forecasts together to understand what the storm is going to feel like. So we still have a lot of work to do in trying to help people understand what the experience is going to be like when you combine all 4 of those hazards together. So just a question to kind of keep in your mind as we move forward. So with that, what I'm going to do is I'm going to stop sharing, and I'm going to introduce Alex Lamers. He's the warning coordination meteorologist at the Weather Prediction Center in Washington, D.C., part of the National Weather Service. And he's going to talk about the rainfall and flooding hazard from tropical cyclones.
Thank you, Robbie. Can you hear me?
We can hear you.
Okay, great. Let's see. Am I allowed to share my screen now? Do I have to get invited to share my screen, or is somebody going to enable that for me?
If you could share your screen, Alex.
Okay. I don't know that I have the option to do that. I'm looking at the settings, and I don't see an option to share my screen.
Okay. We can share from here, and we can we are now sharing your screen, Alex, so you can proceed.
Okay, thanks. I'll just say next slide when I'm ready to advance then. And thanks to Robbie for introducing me. I'm glad to be representing this excellent working group on the topic of forecasting tropical cyclone rainfall and flooding hazards. So I'd like to thank our working group and my co-rapporteur Sunitha Devi of India for their efforts in compiling all the information for this report. I'm also disappointed I was unable to be there in person, I'm happy to talk with you all offline if you have any questions or comments. My email is just my name, alex.lamers@noaa.gov if you're interested in following up. Next slide. Okay, so the topic was not included in the previous IWTC, so we focused on making our report a basic summary of the current state of forecasting TC rainfall and flooding around the world. Each of the topics and slides here could be a lengthy report on its own.
Alex,
actually.
I'm sorry, can you hear me?
Yes.
This is Derek, I'm online. We can't see the slides in the Zoom link. So if someone could fix that, that'd be great.
Okay, I'll stop and.
Yeah, sorry, we could just pause so they could sort that out. You have to pin it. Okay, I got it fixed. Thanks. Thank you, Heather.
Yeah, so if you're online, go to the upper right corner of the thumbnail where the slides are showing and click the little blue screen and pin it.
All right, so I will continue then. Yeah, so I was saying that each of these slides and topics could be really, an entire presentation on its own. And if there's particular topics that deserve that treatment, that may be a focus in future IWTC meetings or international collaboration in the coming years. However, it's very clear that this is an important topic as rainfall and resulting flooding is a common cause of fatalities in tropical cyclones. Robbie just showed you those statistics. And in some regions of the world, it can actually account for a substantial percentage of the total average annual rainfall and extreme rain events, depending on how exactly you categorize that. So therefore, the accuracy and communication of rainfall and flooding forecasts is of critical importance to mitigating impacts. Next slide. So our report identified 8 primary factors that drive rainfall patterns and rainfall intensity in tropical cyclones. These include forward motion of the cyclone, size of the cyclone, topographic enhancements, moisture, instability, the diurnal cycle, vertical wind shear, and interactions with other meteorological features. I won't go into these in detail here. However, I will note that conceptual models based on these factors can be used in combination with other guidance to improve forecasts and convey uncertainties to decision makers. For example, my office uses maps of the climatological distribution of forward speed of tropical cyclones to place a forecast storm motion into appropriate context. A tropical cyclone moving in the slowest 10 to 20% of storms in a given location should be of particular concern from a forecast perspective, and this information can help forecasters determine just how much to emphasize potential extreme scenarios. These factors could also be used to help structure forecaster training initiatives. Next slide. So our working group found a lot of research that was focused around evaluating one or more of the 8 factors that I just described. And more research exists than what we were able to consider or cite in the report. This is just one small example you see here, specifically evaluating the relationship of forward speed and TC intensity to rainfall extremes in certain regions of China. So that's related to some of those factors that I just mentioned. And integrating this type of research into training and workshops is recommended as it can help with applications in specific regions of the world and specific scenarios and helping forecasters understand that. Along these lines, experience and local knowledge were reported to be important in many forecast centers, even if those meteorological relationships had not been formally published in a journal article. However, science sharing through publication or workshops will be beneficial to reinforce those concepts and build the overall knowledge base. Next slide. So numerous forecasting centers reported using or evaluating analog or statistical techniques as a valuable tool in the forecast process. As with any tool, you wouldn't want to use it in isolation, but rather with a combination of guidance. In some cases, the verification results showed that these analog or statistical techniques could actually outperform some numerical weather prediction model guidance. However, that was often based on a comparison with individual deterministic models like the ECMWF or the GFS, instead of ensembles or multi-model ensembles, which are often more skillful. So use that with a little bit of caution. However, it does demonstrate the potential utility of these methods, that they do have value. Next slide. There's basically universal agreement that observations are critical to real-time assessment of TC rainfall, and this is true specifically for the issuance of forecasts and warnings, as well as historical documentation. And that second piece is important because it can be used to refine techniques such as what we just saw. If you want to calibrate a model, either a statistical technique or via some sort of post-processing, having an accurate historical data set is extremely important. Land-based observations tend to be the most reliable, but of course the density of the reporting network will affect its usefulness. Volunteer networks can help fill in data, and they do exist around the world. They may report rainfall only once per day or a few times per day at most, but situational reporting of extreme conditions such as flooded roads or a significant amount of rain in an hour's time can also be helpful and help calibrate what forecasters see in remote sensing data from satellites and radar. Satellite data obviously has far greater spatial coverage, but it's generally limited in its ability to sample the lowest levels of the atmosphere, very near to the surface, which can be an issue in tropical cyclones with dominant warm rain processes. And radar data can provide a more reliable estimate between ground observations, but the coverage is uneven and not available everywhere. Next slide. Overall, a combination of many of those types of observations will provide a more complete picture, and therefore hydrometeorological products that integrate multiple data sets automatically are gaining popularity and use. Theoretically, that would also help remove bias in a more consistent way than a human would be able to achieve alone. We have two examples on this slide, but I'm sure more exist out there. This includes a product from India that integrates satellite and rain gauge data on the left, and on the right, multi-radar, multi-sensor products from the United States, which provide a rainfall analysis, compare that rainfall to thresholds like annual recurrence intervals and flash flood guidance, and produce actual forecasts with a distributed hydrologic model that can provide warning decision aids. Next slide. Another important tool, obviously, is numerical weather prediction model forecasts. These are designed and available in a variety of ways. The global and high resolution models, deterministic models and ensembles, and post-processed products add value and context, particularly to ensemble data. There's a trend toward ensemble information and probabilistic information overall, especially multi-model techniques. Several nations, and this is the case in the US, reported using a starting point for the rainfall forecast that was some version of a weighted blend of a lot of the available model guidance, blending it all together and getting an average and using that as the starting point with some sort of post-processing techniques. And those can be quite skillful. At shorter lead times, high-resolution ensembles are providing valuable information, and that can sharpen forecaster understanding of potential impact areas and high-end rainfall potential, both of which can aid forecast communication to decision makers and the public. So you can see an example here of the Arome ensemble near Madagascar. And finally, I just wanted to note post-processing, obviously very powerful. One clear example is the Extreme Forecast Index from ECMWF, which highlights significant shifts in the ensemble distribution toward the extremes of the model climatology. Next slide. Our team attempted to summarize some key forecast challenges. I'm sure these aren't the only challenges that exist, but these are some of the big ones related to tropical cyclone rainfall. On the topic of models, there is a contrast. Global models obviously cover all areas, but the forecasts are not sufficiently precise around small island countries and fine-scale topographic features. Meanwhile, high-resolution models can fill some of those gaps, but they're not available everywhere. And another challenge is related to observations, of course. Ground observations and radars have highly variable coverage, and that can limit the ability of forecasters to confirm what is going on in certain areas. And finally, there's the issue of rainfall maxima potentially being displaced far from the tropical cyclone center in areas that aren't at direct threat from the core of the tropical cyclone, and therefore they may not be perceived by users as under much of a threat. Even if the forecasts overall are relatively accurate. And so that's both a forecast and a communication challenge. Next slide. And this is an example of what we mean by distant rainfall maximum. This graphic is from USAID, and it shows some areas of heavy rainfall over a 2-week period in November of 2020, with the tracks of two significant hurricanes overlaid, and that's Eta and Iota. And you can see some maxima that are over 500 kilometers from the nearest tropical cyclone center track, one there in southern Mexico and another one down in Panama. And these are generally areas that would not be under an alert for hurricane winds or storm surge, and can even be on completely different coastlines. So you can see how that is a challenge in communicating if they're not under direct threat from the center of the cyclone. Next slide. Something that shows significant promise to help forecasters understand consistent biases, either human-produced forecasts or model guidance, is object-based verification. And we included several examples of that in our report. The example charts you see here were generated for U.S. tropical cyclones by comparing the forecast 2-inch rainfall contour, or 50 millimeters, with the observed 2-inch rainfall contour. And we're basically seeing how far off the centroids of those two objects are. And in a way, it's similar to the method you would use to calculate forecast track error for tropical cyclones. We're just doing it for rainfall. And these charts allow us to see the observed heavy rainfall areas tend to be slightly offset to the northeast and east of where they're forecast. And that's at all forecast projections. The darker and colder colors here indicate smaller distance errors on day one. The lighter and warmer colors indicate larger distance errors. And the size of each of these wedges indicates how often that direction of displacement error occurs. So generally, the directional error is pretty consistent, but it tends to be larger with longer lead times, as you would expect. And forecasters could use this information to correct for bias over time. In this particular example, and for the US, our theory is that the vertical wind shear vectors are commonly from the west to the east in and around the US. And so models and humans often underestimate how much this will push the heaviest rain east of the storm center. Next slide. When it comes to warnings, many countries reported tiered warning systems for rainfall and or flooding. The working group did find several nations are integrating the warning systems with mobile device alerting, and we only got several examples into the report, but there may be more that exist out there, and that can help with broader distribution. The two examples here are, one is from Japan, which used a 1 kilometer real-time risk map with different colors to indicate the current and predicted risk level at each location. And the risk distribution is used to supplement official weather warnings. And another example on the bottom is the wireless emergency alerts in use in the United States, which automatically sends official warnings and short messages to mobile phones. And another tool I don't have on the slide here in picture form is the excessive rainfall outlook, which I'm happy to chat more about since my office is heavily involved in producing that. It's not necessarily a formal warning, but it is a probabilistic and impact-focused forecast, and it provides the probability of flash flooding within 40 kilometers of a point for each day of the forecast. And verification shows the probabilities are reliable, so it can provide useful information on potential impacts, and that goes beyond the standard forecast of rainfall amounts. So we've gotten a lot of traction with that lately here in the US. Next slide. Thresholds can be a useful way to frame rainfall information. Beyond a given threshold, an impact, generally flooding, but could be something else like landslides, can reasonably be expected. But of course, there's always some uncertainty associated with that. Picking a single value may not capture the full variety of hydrologic complexity in a given area or a basin. And of course, the threshold itself is often an estimate. It may not be precisely when impacts occur. In other words, it's not like flipping a switch and flooding will suddenly occur. But overall, I think thresholds can help forecasters understand rainfall forecast guidance and observations in context, and incorporate that into their forecast warnings and communication. A global flash flood guidance initiative is attempting to expand the availability of flash flood guidance, and that's generally an estimate of the rain rate that would be required to generate flash flooding. And things like average annual recurrence intervals can also be used to understand the potential for rare or unusual rainfall. Next slide. The complexity of hydrology and the different approaches to hydrologic information is something that I think would benefit from a more focused treatment in future IWTCs. It was just a small component of what we were able to produce in our report, but we were able to determine the approaches vary quite a bit from country to country, and this includes anything from physical models to statistical models. And understanding best practices with respect to river and stream forecasts, particularly in areas without many operational river and stream gauges, is important. A 2011 study from Kumu et al. Calculated over half the global population lives within just 3 kilometers of a body of fresh water. So in many cases, the magnitude and placement of rainfall will be the dominant uncertainty, but other hydrologic uncertainties are important. And that all feeds into getting accurate flood information for all those people that live close to rivers and streams. I do think that quantifying those uncertainties and displaying them in useful formats, such as flood and inundation maps, shows significant promise. Probabilistic formats, like you see an example here from the Global Flood Awareness System, from the Copernicus program, also very useful. And finally, collaboration between meteorologists and hydrologists can be very beneficial, and ways to improve that should be strongly considered. Next slide. So I believe the agenda said we'd be discussing recommendations tomorrow. I'm not going to go into those in detail here, but I did at least want to show them. And a lot of them are related to increasing the availability and quality of information for forecasters. We did also emphasize the need for collaboration, like I said, between meteorologists and hydrologists. And another thing that we may want to give consideration to is expanding the amount of information available in our official tropical cyclone databases. The Best Track archive, for instance, is very focused around the core TC metrics, such as maximum sustained wind, central pressure, and location of the center. And thinking about creative ways we may be able to integrate something like the highest rainfall observation or set of observations could be useful and signal to the global community there's other vital historical components to the TC record that we may want to preserve. Next slide. And final slide here. We also expressed a desire that tropical cyclone workshops and training courses continue to fully integrate rainfall and flood components. We know this is being done in a lot of cases, but we should make sure it's standard practice. However, I do think it's worth considering whether we could take that a step further as a global community. I included a map here showing flood disasters logged in the International Disaster Database. And the map is somewhat dated at this point, but it does illustrate the key point, which is basically that every country in the world can experience flood disasters. And therefore, our group thought that it may be worthwhile to expand the availability of workshops and training courses that speak to rainfall and flood forecasting best practices in general, not just for tropical cyclones, as some best practices are likely to be broadly applicable to all countries. And with that, you can go to the next slide, and that's it from my presentation. Thank you for your attention and your invitation to be involved in this conference.
Thank you, Alex, and your team for compiling all the information. And we request you to please stay online for the questions after the session. And now I request next group team, Ms. Andri Shumeka and Craig Earlspur from Bureau of Meteorology, Australia. Yeah.
Okay, thank you. As Monica mentioned, I'm Craig Earlspur from the Bureau of Meteorology. Our topic focusing on the wind aspects of forecasting hazards and impacts. I mentioned Andrea Schumacher, really enjoyed working with her in particular in this group, but to all of our working group as well, I want to thank them for their efforts. Once again, with this being a new topic, we've kind of taken the approach of having a look at what the various practices are across the different parts of the world, with a little bit of a focus on some of the more recent stuff and a few of the better examples that we've found. But I wanted to start off by kind of being clear on what we're talking about when we're considering a wind hazard forecast. We know that wind forms part of the definition of tropical cyclones across all basins. We've heard in the previous days about structure, intensity, all these parts of a tropical cyclone that the wind hazard is basically built upon and how we consider it. And we know that all this sort of information is contained in all our tropical cyclone forecasts. So this is just an example from India. I'm sure you're all familiar with these. They're very similar right across the globe. But the key thing is that for those of us in this room, we know there's a wealth of wind information in there, but that's because we understand tropical cyclones better than the rest of the community. And we can't assume that they're getting the same understanding of the hazard they're facing from these sorts of products. So while the tropical cyclone forecast has a lot of information on wind, it's not a wind forecast. So then what is a wind forecast? Really, we want it to be complementing the rest of the tropical cyclone products that we're sending out. But the key part is it's explicitly talking about the wind information and focusing on the location of the user of the product. So rather than taking it from a system-centric point of view, it's the question for if we were facing an event now, what's the wind going to be here as this event unfolds? That way we're reducing the need for the interpretation of the end user. They don't need to understand the cyclone as well. Of course, some understanding is always going to be helpful, but the less that they need to know the full ins and outs of a tropical cyclone, the more likely they are going to be able to take an action to respond to the threat of the wind hazard. The other key part about wind hazards is a valuable input into hazard modelling and also secondary impacts. So we know that we want to know more about the wind when we're looking at waves and storm surge, for example. We've already heard a fair bit about the impact side of things, and so I'll just re-emphasize the part about incorporating the exposure and vulnerability information. So if we start to think about putting together the surface wind field, the two main approaches that we see is high resolution NWP, and while that's been improving year on year, it still struggles to resolve the really extreme features near the convective inner core of a cyclone. For that reason, parametric modelling tends to be the preferred approach, and there's a number of different solutions out there. We don't have time to go through all of them. I've got here an example of something that's being worked on in the US, which is resolving a really high detailed wind field in tropical cyclone events. And the benefits of a parametric model, not only are they much simpler than NWP, they give a pretty good result. They're going to be consistent with the forecast track because they're built from the forecast track. And there's also, I want to mention the fact that while there are a lot of different versions of parametric models, the application that you want to use it for is really critical in terms of which one you want to use. There's strengths and weaknesses to each of them, and so it needs to be well considered. What is the next step that we're taking? What do we need this wind hazard information for when choosing a parametric model to use? So one other part that I'll mention is that one extra benefit of the parametric models over NWP is that NWP is more subject to biases, whereas the parametric shouldn't have those as much. Now, the downside of a parametric model is that it doesn't really account for the uncertainty in the forecast. And when we're talking about the wind hazard, we know that it's very sensitive to a number of different uncertainties. So whether that be the track, the timing, the radius of the maximum winds, all of these things, they can compound on each other. And looking at consecutive runs of a parametric model on a different forecast track can lead to a very big difference in the final wind hazard output that the end user sees. And so probabilistic forecasts, we've heard a fair bit about them this week as well. Obviously they're the best way we know of at the moment of really trying to quantify uncertainty in our forecasts. And they are more consistent with a risk-based approach to responding to the hazard. This example is the 50-knot wind probability from JMA. So this was taken just earlier this year. And I'm sure people are familiar with many of these. The wind speed probability products in the US is probably the best known. But the majority of them that we see, they're a statistical approach to it. And so they don't consider the situation-dependent parts, very similar to what we saw yesterday in considering the confidence areas when putting together a forecast track. So just want to talk about a couple of examples of using the dynamic ensembles to try and account for that situation dependence. The first one is relates to this image here. This is the spicy project that has been done in La Reunion. And it starts off with a statistical approach in the terms that it's applying past track errors, forecast track errors, to the latest forecast track to develop a number of scenarios. But then there's probabilities associated with each scenario, and those probabilities get modulated based on the ensembles that are available. So at the end, by modulating it, you're getting a more dynamic input into the final product. This project was based on working towards impact-based forecasts as well. So it's one of the two examples that we've discussed in our report of really trying to account for situation dependence when putting together that uncertainty in a wind hazard forecast. The second example is one from Australia, and this one's taking a slightly different approach where rather than starting with the official forecast track, it's starting with the ensemble output, and then it applies a statistical correction to the ensemble in order to resolve the finer features that a NWP model struggles to get. And in both cases, they feed the downstream products, they provide the wind speed probabilities. Probably one of the most significant differences is that the Australian example doesn't rely on having an official forecast track. So you can start producing these long before you've got your track, so you get more of an end-to-end from genesis through to the actual event in terms of being able to communicate wind hazard in a probabilistic sense. Now, if we move on to impacts and really the wind hazard modelling, this becomes a logical next step. Once we've quantified our wind hazard, we want to try and incorporate the exposure and vulnerability information that we have available to try and put together an impact-based forecast. So this is one that we found is generally very much still in its infancy, well, in our opinion anyway, in terms of really getting that exposure and vulnerability information in. A few reasons for this is just trying to get that information can be a challenge. But the two examples that we've discussed in our report, this is one again from Australia. So this is actually Geoscience Australia who have put together this. So they've got using a parametric model that's based on the Bureau forecast. They then have the database of exposed assets. So it's generally looking at buildings and structures, and then it calculates from that wind hazard and the database of exposed assets what the likely level of damage is. And so you can see the shading of the colours from this Seroja example, how we've got the red areas where we're expecting significant to near complete damage, and some of the places a little further away from the strongest winds, negligible or even just slight damage. And it can be aggregated, so here it's at essentially a shire, a local government level on this map, but it can then be done at a state level. It puts it into a dollar value, and it helps emergency management agencies make decisions in terms of deploying assets and preparing for response and recovery. The other example that we had is from IMD. They're called the Dynamic Composite Risk Atlas, and very similar in the way that it has the wind hazard from the model. They've got databases on various socioeconomic factors, so considering things like population, housing density, various utilities that may be in the way, even road networks. Once again, it has a quantitative output of what sort of damage you can expect for those various assets and aggregates them at different levels. Now, I think a common theme that we've heard from this morning in impact-based forecasting is that there's been a lot of challenges. the WMO guidelines, I think that's a really good document. It really spells out how to go about it, but that doesn't make it easy to do. Exposure and vulnerability data, it's not normally held by weather services, and the guidelines, they are well aware of that, but it means you need to find who does hold them. You need to build the relationships with those people. You need to find ways to make your data sets compatible. Different agencies can have different priorities, and so therefore, while you may be going to them wanting to work, they may have other things that they want to focus on instead. And it's really key thing that multidisciplinary design, so forming these partnerships, was the feedback that we got was a very consistent theme coming out of it, that you really need to have these good partnerships with the other agencies if you're going to do this and make it work well. And in terms of those data sets as well, I think wind is actually a really tricky one in the sense that wind, it'll be everywhere. It's all pervasive. When we talk about some of the other hazards, rainfall, we mostly are concerned about it when it's over the land. We get really concerned about it when it's falling in various catchments that are very prone to flooding. When it comes to coastal hazards, it's limited to the coast or waves out at sea. Wind is across all of these places, and the various impacts that wind can have likely need different approaches in terms of trying to model them and create those impact-based forecasts. The other thing that stood out to us from the two examples that we've discussed in the report of impact-based forecasts is they're both taking a deterministic hazard forecast to build them. They're not incorporating the uncertainty information that we see from the probabilistic products. And as mentioned, with high sensitivity to the forecast for the wind hazard, it seems that we really need to have that uncertainty better incorporated into any impact-based forecast that we're producing. Finally, on this slide, I just wanted to mention that it seems that impact-based forecasts are progressing a lot more in other hazard areas. Heatwave is a really key one where there seems to be a lot of examples of well-matured heatwave impact-based forecasts compared to tropical cyclone. So just to summarize all the stuff we've been through, we want to really be focusing on the end user when we talk about wind hazards and impacts. So less on the system itself, and more on where it's going to hit and what the people who are in harm's way need to prepare for. The parametric wind fields are a simple and effective way of putting together a wind hazard forecast, but the probabilistic forecasts are really important for accounting for uncertainty. And there's been some good advancements in the probabilistic forecasts that are incorporating both the dynamic ensembles rather than being just a statistical approach. And finally, there's still plenty of challenges that we are facing along the road to implementing impact-based forecasts. And that's all I prepared. I'll leave it at that, and we'll leave the recommendations for later. Thank you.
Thank you, Craig. The next topic is storm surge hazard. So Dr. Nardo Kohano from JMA, he'll be presenting his report.
Thank you, Monica. Hello, everybody. I'm Nadao of Japan Meteorological Agency, and I talk about the recent progress and the activities on coastal inundation or storm surges. And here is the list of the working group members. So although number is not so many, but we fortunately we have a very resourceful person, so we managed to create significant report. This is the outline of the contents. Start with introduction. I introduce some recent advances and summary and conclusion, and end with recommendations. First of all, this is the recent major storm surge cases generated by tropical cyclones. And I highlighted fatalities with blue color, which is larger than 1,000. And you can see recently the number of fatalities is not so many comparing with previous results. I also mentioned that so the number is not indicate only killed by storm surge. Some other the fatalities caused by other effect is also included in many cases. But please have a look at numbers. So it's basically it's lower than 100. And comparing with the previous cases, storm surge killed so many people. And I would like to remind you, 2 years ago, 2020 was half-century anniversary after the deadliest storm surge cases. In 1970s, severe cyclone hit the coast of Bay of Bengal and killed 300,000 to 500,000 people. So, which was the deadly cyclone cases. And after that, only 2 storm surge cases killed more than 100,000 people, like cyclone in 1991 or cyclone Nargis in 2008. All happened in North Indian Ocean, actually. And also, so therefore, number of fatalities dramatically decreasing. But sometimes storm surge generated quite large economic losses. Although this is just the amount of economic losses, and some is not so large, but it is quite significant considering of the country GDPs. Anyway. So as we have looked at the recent cases, storm surge is one of the key hazards associated with tropical cyclones. As Robbie showed, studies have shown that nearly half of the fatalities in US are caused by storm surges. And storm surge have devastated many parts of the world, especially in North Indian Ocean. But death toll is remarkably decreased in recent cases. As we have seen, recent death toll is lower than 100. However, economic loss are sometimes huge. And we can believe that those improvements may partly come from improvement of warning service on coastal hazard. Anyway, we are highlight the current and the recent advancement in this field. First of all, in storm surge forecast, many national met service cooperate with forecast uncertainty. Storm surge are strongly dependent on the landfall location, intensity of TCs. So therefore, accurate TC forecast is essential. However, it is impossible to remove forecast errors in real. So we need to deal with this forecast uncertainty. The one practical solution is, of course, probabilistic forecast, or at least merge scenario forecast. And such forecasts were introduced in many national met service, US, Japan, Australia, Canada, and those forecast system is will be planned in FMS and Fiji and India. Here's the lower graph is the sample of those probabilistic approach. Basically, we assume several cyclone tracks and calculate possible storm surges with those members. As for National Hurricane Center of US, they also change tropical cyclone intensity and size. And the right panel is the planned multi-scenario cases at FMS, which will be introduced in this coming cyclone season. They also consider some possible case right-hand side or left-hand side, as well as the possible official forecast. And as for the BOM, they actually calculate quite huge number of ensemble members. They basically could suppose 1,000 possible tasks and randomly extract from the 1,000 possible tracks, they extract 200 ensembles and conduct storm surge simulation. As for storm surge probabilistic forecast approach, this is the ROC curve evaluated by National Hurricane Center. And the curve indicates the probability of exceedance. And the value indicates the ratio of probability of exceedance. And the horizontal axis indicates false alarm rate, and vertical axis indicates probability detection. So as you can see, 0.5, which is the 50% of the probability of exceedance, is not so well work. However, if the threshold to change to 0.1, 10% exceedance of exceed, then will work well. So therefore, such probabilistic approach will be surely effective. Based on such probabilistic approach evaluation, many national met service shifted their information to more indicating real risk, namely coastal inundation risk. And now, currently, NHC issued coastal flood risk map shown like this, based on the 10% probability of exceedance, which is determined from the previous analysis. And also, IMD issued such coastal inundation map. The right one is actually it's the prototype created in the research project, strategic innovation promotion program of Japan. And although it is, and it create quite detailed inundation areas. And this is actually a research project, but the success will be evaluated whether the result will be put in operation. So therefore, this research project is aiming to operationalization. So even though such detailed inundation risk map is not provided, recently National Met Service have been indicating coastal hazard risk with map images. The right one is the map image of Pagasa, Philippines. And you can see several color lines in the coastal region where storm surge is feared. And also, Meteorological Service of Canada produce similar map images. So therefore, these maps clearly indicate the really vulnerable coast, which will be very effective for public people. And besides providing such coastal inundation risk, several national met service also try to provide further information. This is the information issued by Pagasa. So basically, the left column indicates storm surge height, and also possible areas are listed. The right two side is quite impressive. The second one, first one is the describe detailed impact. And the last one is suggest desirable actions, actually. So therefore, not only describing the possible risk, but also their concrete impact and necessary actions are provided operationally. So as you know, it is quite a difficult task, and Pagasa work hard in creating these information. And a similar approach was ongoing in Canada. So the Meteorological Service of Canada now creating a coastal flood risk index. So of course, it is a little bit difficult to read also. I don't expect it. But I would like to show this idea indicates possible conditions and also their concrete impact and suggested actions are summarized as a standard table. So which will be very useful in future for the people in Canada. And there are several other improvements, so I'd like to show them. The key point is that several improvements are done based on the request or requirement of disaster management authorities. And this is one case of Japan 5-day perspective. It's referred to as probability of warning. So JMA started to issue probability of storm surge warning last August. And probability of storm surge warning is indicated qualitatively by high or middle. It's vague information, but such information ahead of 5 days can be used for disaster management authorities who are preparing for their shift plan and so on. So therefore, even though the information is not so concrete, it will work well. And also BOM basically provide worst case scenario, storm type cases. However, they also provide special case scenarios based on the request of emergency managers. So recently, National Met Service tried to improve their information based on the requirement of disaster management authorities. And as for other improvement, so I rather focus on the improvement on information, but of course, those information based on forecasting system. And the improvement in forecasting systems are summarized like this for introducing higher resolution models and the integration of coupled dynamical models and so on. So for introducing higher resolution models, so recently unstructured storm surge models are introduced in many several operating centers. And India Inquas operate advanced circulation model for real-time storm surge forecast and so on. And there is a interesting trend in research, and National Oceanographic Service tend to focus on developing sophisticated storm surge models. And the most inner grid resolution in the most inner part is around 50 meters or so. So they are rather focused to create detailed hazard risk in coastal region. On the contrary, National Met Service is rather focused face to uncertainty of tropical cyclone forecast. So many national service rather stress in increasing ensemble members and so on. Of course, both are important topics, but available resource is not unlimited. So we need to focus some of them. So anyway, I would like to comment to trend between National Met Service and research or oceanographic service. This is a summary and conclusion. So anyway, this recently some information on coastal hazard has good progress, and many national service try to introduce probabilistic information, forecast, and also they try to shift their information more impact-based oriented information. And as for recommendations, I do not read in detail, but several key points I would like to mention. So the first priority could be to introduce more ensemble forecast. Actually, which is aligning with the TCPFP Helen introduced yesterday. So therefore, this is really this will be good recommendation. And of course, we need to improve our storm surge information, but this should be based on the request from the disaster management authority and so on. And also for better information, we need to develop forecasting systems. And also, I didn't explain it, but according to the previous survey, in many countries, the number of tide cages is quite small. So it is not sufficient for monitoring real-time condition and also verification for further improvement. So therefore, introducing more tide observation could be crucial. And the last one is related to the previous presentation. The storm surge is generated mainly by stormy wind. So improvement of wind field is crucial. That is all. Thank you.
Thank you, Dr. Nado, Dr. Cody, and your entire team for summarizing the progress on storm surge hazard. Now, the next topic is hazard due to TC tornadoes. Dr. Derek Carroll Smith from JSU, NCR, USA, and Dr. Benjamin Green from NOAA, USA. They'll be presenting the progress with respect to this topic. So I request WMO team to please play the video they have sent.
Hello, I'm Derek Carroll. I, along with my co-rapporteur, Ben Crane, will summarize research and operations related to tropical cyclone-spawned tornadoes. Before we begin, we would like to give thanks to our working group members and their contributions, as well as the topic leads. Tornadoes are one of the secondary and lesser research hazards contributing to the devastation TCs leave in their wake. While gale force winds and storm surge produce the majority of damage and fatalities globally, TC tornadoes also pose a fatal threat, complicating evacuation plans and protective actions as the storm moves inland. Climatological studies characterize TC-spawned tornadoes as weak and short-lived, primarily originating from miniature supercells in the outer rain bands. This makes forecasting and radar detection particularly challenging. Additionally, TC tornadoes can pose a threat to communities 12 hours prior to and beyond 48 hours after a TC makes landfall.
I'm sorry to interrupt, but online there's no sound. Can you stop the video, please?
Yeah, we're trying to just solve the sound problem, everyone. It's not just online.
Do you want? Oh, okay. Do you want me to just play it through my computer? Because I can try to do that.
Okay, we'll give that one a go. Yeah, thank you, Ben.
All right. Sorry, 1 minute to do that. Yeah, it was 1 minute. Oh, it is not. Let's... One minute, please. Sorry. Erica, are you able to play the video? I'm having some issues with share screen. I apologize.
We will play it. We have another option here, just playing it in the room.
I think my colleague is going to try to share.
Carroll. I, along with my co-rapporteur, Ben Crane, will summarize research and operations related to tropical cyclone-spawned tornadoes. Before we begin, we would like to give thanks to our working group members and their contributions, as well as the topic leads. Tornadoes are one of the secondary and lesser research hazards contributing to the devastation TCs leave in their wake. While gale force winds and storm surge produce the majority of damage and fatalities globally, TC tornadoes also pose a fatal threat, complicating evacuation plans and protective actions as the storm moves inland. Climatological studies characterize TC-spawned tornadoes as weak and short-lived, primarily originating from miniature supercells in the outer rain bands. This makes forecasting and radar detection particularly challenging. Additionally, TC tornadoes can pose a threat to communities 12 hours prior to and beyond 48 hours after a TC makes landfall. Research, both basic and operational, has increased globally over the last few years with cyclone-spawned tornadoes. Hello, I'm Derek Carroll. I, along with my co-rapporteur, Ben Crane, will summarize research and operations related to tropical cyclone-spawned tornadoes. Before we begin, we would like to give thanks to our working group members and their contributions, as well as the topic leads. Tornadoes are one of the secondary and lesser research hazards contributing to the devastation TCs leave in their wake. While gale force winds and storm surge produce the majority of damage and fatalities globally, TC tornadoes also pose a fatal threat, complicating evacuation plans and protective actions as the storm moves inland. Climatological studies characterize TC-spawn tornadoes as weak and short-lived, primarily originating from miniature supercells in the outer rain bands. This makes forecasting and radar detection particularly challenging. Additionally, TC tornadoes can pose a threat to communities 12 hours prior to and beyond 48 hours after a TC makes landfall. Research, both basic and operational, has increased globally over the last few years in efforts to move from a climatological to ingredients-based approach to detect and forecast TC tornadoes. While the United States has led the charge, given the increased exposure to tornadoes year-round, other nations such as China, Japan, and Australia have increased their efforts to record and detect TC tornadoes. Despite these advancements, more work needs to be done globally to understand a TC environment conducive for tornadic activity. Globally, TCs have been reported in various regions across the world. However, only China, Japan, and the US have seen more than 10 tropical cyclones that produce tornadoes, with the largest record in the US. This is likely due to undercounting due to tornado damage and debris concealed by damages from the more primary TC hazards. Undercounting is also a result from lack of radar coverage in the more remote regions and the relatively short period of standardized tornado records, if they exist at all. The U.S. developed a TC tornado archive documenting 1,745 tornadoes between 1995 to 2021. This archive is updated yearly, so feel free to scan the QR code for access to that database. The complete record goes back to 1955. However, TC-TOR was designed to align with the advancements of the WSR-88D and dual-pole radars that are used to detect and verify tornadoes. From what we could gather from the other countries, China averages about 5 TC tornadoes a year, and Australia recorded tornadoes from 3 tropical cyclones and 3 post-tropical cyclones, while also recording many tornadoes from tropical lows. Nevertheless, China and the U.S. have substantially more TC tornadoes than any other nation. Climatological studies, particularly in the Northern Hemisphere, have shown that TCTs can occur up to 12 hours before and in some cases beyond 48 hours after the storm makes landfall, favoring the late morning through afternoon hours. TCs that recurve into the mid-latitudes were associated with the more prolific tornado outbreaks. The majority of TCTs occur within the outer rain bands between 200 and 400 kilometers from the TC center, typically favoring the northeast quadrant. The most recent studies found that this quadrant has the environmental ingredients needed for TCT development. The figure on the right shows Cape and Helicity in tornadic TCs in the far left column, non-tornadic TCs in the middle column, and the difference between the two in the far right column, illustrating that tornadic TC environments have more buoyancy and shear than non-tornadic TC environments. Furthermore, 85% of TC tornadoes documented specifically in the U.S. are spawned by miniature supercells, discrete cells, and linear convective systems. The supercells are considered miniature given the shorter cell height and rotating core compared to what has been observed in mid-latitude supercells, and that is the figure that you see in the schematic on the right. In addition to moderate cape and shear, other environmental factors associated with TCTs include a lower lifting condensation level, dry air intrusions, and the interaction of the tropical cyclone interacting with baroclinic boundaries. Previous studies have investigated the role of deep layer vertical wind shear in tornado development. Deep and shallow low-level shear is enhanced with the interaction of the TC with the mid-latitude trough. In the northern hemisphere, southwesterly shear focuses tornadic convection in the northeast quadrant of the TC. The schematic shown is a conceptual model of the deep shear influence in tornado favoring TC scale convective asymmetries. Stronger ambient deep shear boosts TC tornado potential by supporting larger, longer-lived convective development in favorable parameter spaces of Cape and in large lower tropospheric hodographs. Finally, in the U.S. and observed in other countries, TC tornadoes are weaker than their mid-latitude counterparts, with most tornadoes rated lower on the EF scale. These tornadoes primarily develop along the coast. However, stronger tornadoes have occurred, many of which further inland and often are spawned during the extratropical transition period. Now I will hand it over to my colleague to report on the operations perspective.
So now we're going to move on to operations. We decided to use the United States as an example because they experience more tornadoes, both from tropical cyclones and from other sources, than any other nation. We do acknowledge that every nation does things differently, but we feel that the United States would provide a great example. So the concept of the forecast funnel is that you make more specific forecasts as you get closer to an event. With that in mind, out to 72 hours before a tropical cyclone makes landfall, the Storm Prediction Center coordinates with the National Hurricane Center to get a forecast of tropical cyclone location and then outlines a broad area of TC tour risk based on climatology, which is typically the northeast quadrant. Then as we move closer to the event, tornado watches are issued on the day of the tornado threat, typically with lead times of up to 12 or 16 hours in tropical cyclone environments. The SPC uses an ingredients-based approach, where is the best buoyancy and shear, to outline an area that is most favorable for TC tours, and they coordinate with local weather forecast offices to issue the tornado watch. Tornado warnings are short-fused with lead times of no more than 1 hour. The local weather forecast office uses dual polarization Doppler radar, trained spotters, and public reports to issue a localized, cell-specific warning when a TC tour is imminent or ongoing. So I mentioned dual polarization radar, Doppler radar. Doppler radars, especially those with dual polarization, can vastly improve detection of tornadoes both in tropical cyclones and in other environments. And I'm using this example from Hurricane Irene in 2011. This image is the base reflectivity, and it's very hard to see any sign of a tornado. If we look at the velocity product provided by the Doppler component of the radar, we do see a velocity couplet towards the middle of the figure. But then these two bottom products are from the dual polarization capabilities, and particularly the cross-correlation coefficient in the bottom right panel provides a great idea of where a tornado is located. And in fact, there actually was a tornado at this location. So communicating tropical cyclone tornado risk, what are some best practices? We talked with various operational centers around the globe. In Australia, they assess threats separately with unique community action plans for individual risk thresholds. And tornadoes are typically assigned lower risk due to their rarity and also the broader risk posed by other tropical cyclone hazard threats, namely gradient wind and storm surge. The United States provides ready-to-use text for NOAA weather radio, emergency broadcasting, social and traditional media, which details hazard, timing, and location, and they can use impact-based warnings and assign a different damage tag based on the perceived impact. So something that is very important with tropical cyclone tornadoes is that there's other ongoing hazards, and overlapping threats can cause confusion and contradictory emergency messages. Damaging winds, either from a tornado or from the larger scale gradient flow, can overlap with flooding. So the advice given for wind, which is to shelter in the interior lowest level of a building, is dangerous when the ground floor is or may become inundated by floodwaters or storm surge. And this is an issue in non-tornadic tropical cyclones and also just other non-tropical cyclone environments. And the US Weather Service, as well as other governments, are working on this issue. So on the right here is a figure that is showing an overlap in tornado warnings in red and flash flood warnings in green issued during Hurricane Harvey. In other words, there are a lot of places and times where tornado warnings were ongoing with flash flood warnings, and this posed a communications problem to the public. So, limitations and future developments. Dual polarization Doppler radar coverage is limited in many nations. Some, like Australia and China, are investing in expanding their coverage. There is ongoing work worldwide to modernize hazardous weather warning messaging. The Bureau of Meteorology is working to develop and implement an Australian warning service. China is in the early stages of more robust tornado prediction and warning protocols. The United States is planning to develop more specific and clear threat messaging for tropical cyclones with multiple concurrent hazards. Various nations have increased their reliance on high-resolution numerical model guidance for hazardous weather warnings, and some examples are listed here. But there has not been yet a systematic evaluation of this high-resolution NWP in TC tour situations. So to summarize and conclude, tropical cyclone tornadoes are indeed a global threat, but are by far much more common in the United States and China. The median TC tour is weaker than the median non-tropical cyclone tornado. TC tours are often spawned by miniature supercells, which in the Northern Hemisphere are favored in the northeast quadrant of the tropical cyclone, where shear and instability are highest. Tornado forecasting benefits from treating the tropical cyclone as a time-evolving, large-scale forcing, rather than as a static, monolithic entity. The United States has established protocols to forecast, detect, warn, verify, and document TC tours. Other countries do not have such a robust end-to-end framework due to rarity of tornadoes, tropical cyclone or otherwise, as well as gaps in radar coverage, particularly Doppler and dual polarization. And also concurrent tropical cyclone hazards can cause confusion in communicating risk. So recommendations. Very early on, it became clear that there is a need for a comprehensive global tornado database, not just for tropical cyclones. Few nations maintain any easily accessible comprehensive tornado database. Having a global tornado database with agreed upon minimum standards would greatly improve research efforts for all tornado environments. There's lots of new and emerging technologies to detect tornadoes, including TC tours. The biggest one of these is dual-pole Doppler radar, but we acknowledge that those can be extremely expensive and not every country has the resources to implement those. Lightning products from high-resolution satellite imagery can also prove useful in TC tour detection, especially in areas without radar coverage. And finally, social media images and videos can help document TC tornadoes in real time. The future of research into tropical cyclone tornadoes, we really want to get a better understanding of why some TCs produce 100 or more tornadoes, while others of similar size and intensity produce few to none. Also, emerging technologies such as drones could aid in rapid deployment of field campaigns, particularly in hostile or dangerous conditions. So with that, thank you very much for your time.
Thank you, Dr. Carroll and Dr. Green and your entire team for summarizing the progress on TC-related tornadoes. Thank you very much. So now, as topic lead, myself and my co-lead, Mr. Robbie Burke, will be presenting the current status, gap areas and challenges, and the recommendations with respect to our topic on forecasting hazards and impacts. So this has already been discussed that most of the deaths, 9 out of 10 TC deaths are due to water. So based on the review we have conducted, it is seen that TC science, improvements in TC science definitely lead to better decision making, not only by the forecasters, but also by the users and the customers. The TC forecasters, they develop probabilistic data for all hazards at varying spatial scales for issue of watches and warnings using risk paradigms, including the hazard-based modeling and risk and assessment. And the customers, the users, they are not interested in knowing what the weather will be. Rather, they want the information about the impact and the associated risk as per the thresholds decided by them. And we have identified various challenges and gap areas for impact-based forecast, and in the role of social science research and best practices for improving the IBF. And this is typical example from USA. And the studies show that all the NMHs, they have not been able to incorporate impact-based forecast so far. Some of them have already developed using probabilistic guidance that accounts for uncertainty in the individual hazards. However, it is not uniform over the globe because of a lack of tools and technology and data and methodology. And here we have shown the example from USA. NWS USA is providing interactive hurricane threats and impact maps, and they are providing information about what the users should be concerned about, where a particular hazard is expected, what will be the duration of the hazard, and what will be the time of occurrence, and what should they be prepared for. In addition, they also provide impact statement and hazard-based threat information. With respect to storm surge, USA is providing storm surge warnings and storm surge watches. If you consider the example in India, IMD is providing the hazard over a particular region for various thresholds, and in addition to that, they are also providing the population likely to be affected, and they have also quantified the various exposure elements that are going to be affected by the hazard and the loss in terms of money. That has led the government to release pre-disaster relief funds to the affected states. In Australia, Bureau of Meteorology is providing the damage to, this particular example shows the damage to buildings in terms of various thresholds as moderate, intense, extensive, or complete damage. However, there is still scope to improve. And we need to adopt a uniform user and hazard specific impact-based forecast with socio-economic data. And considering the multi-hazard nature of TCs, we need to develop a multi-hazard early warning system and impact-based forecast. And it is seen that no individual NMHS can independently develop IBF. It has to be a multi-institutional mechanism involving the meteorologists, the researchers, the disaster managers, and the stakeholders. And currently it is seen that there is lack of institutional mechanism and guidelines in many NMHS for multi-hazard early warning system and IBF. And there is also need to incorporate the impact of climate change while developing IBF. And there is also need to integrate multi-hazard early warning system and IBF with each stage of disaster, like pre-disaster, during disaster, post-disaster, and response actions. Next comes the development of impact-based forecast module on GIS platform for decision making. Currently, many countries have introduced, but it is not uniform throughout, mainly because many of the developing or least developed countries, they lack the the data and technology information for development of IBF module. And also because apart from the meteorological data, they lack the vulnerability and exposure data for development of IBF. And this is the figure on the left. It shows how IBF can be developed by incorporating the meteorological information on geophysical data, exposure, and vulnerability elements. So considering all these gap areas and challenges, what we have found that there is need to establish a value chain that incorporates all the aspects of early warning system, including the observations, modeling, forecasting, severe weather warning, sectoral applications, and including research and development also. And in addition, artificial intelligence and machine learning applications, they can be utilized in conjunction with NWP modeling. That is, a dual engine concept can be experimented for developing probabilistic forecasting of TC hazards, impact-based forecasting, and risk-based warnings, and for improving last mile connectivity. So with that, I request my co-lead, Mr. Robbie, to please present the recommendations.
Hey, thank you, Monica. So I'll go through these fairly quickly in the interest of time, but we have 5 recommendations, essentially where we tried to consolidate the various recommendations that came from each of the subtopics, each of the hazards. And so for recommendation number 1, I'm not sure if if screen is still showing or if I'm supposed to share. There we go. Okay. So recommendation number 1 is that nations should set up or leverage joint multi-institutional mechanisms involving operations and research communities, as well as disaster management agencies, to effectively communicate and mitigate TC hazards. Essentially, that we as meteorologists can't do it alone. And I think there's a lot to be learned from the disaster management community, from disaster science. There's probably lots of ideas that we're just not even aware of, and how we can better effectively communicate these hazards. There are some considerations, obviously, that frameworks may be different from country to country. And IBF, as we know it now, may or may not be available in all countries as well. Okay, next slide. So recommendation number 2 is to improve disaster risk knowledge through the detection, monitoring, analysis, and forecasting of tropical cyclone hazards, vulnerability, and their consequences. I think there's several considerations here. One is, we already talked about this, is that there are multiple hazards and they can occur differently across time and space. And so that really needs to get a closer look, and that we're not just looking at silos of 4 or 5 different hazards. As you saw in the presentations, there's a big increase in the use of probabilistic hazard guidance, which is great. But we have to consider what those probabilities mean. In other words, a 20% chance of something doesn't mean the same thing. It depends on what hazard you're talking about. So, for example, a 20% chance of rain is not the same thing as a 20% chance of an 8-foot or 2.5-meter storm surge. So while we're producing probabilistic guidance, we have to be translators of those numbers, of those probabilities, so that our publics and our users understand what the risk is for those probabilities and the particular hazard that we're addressing. And lastly here, I would say that historically we've used categorizations to classify storms. Here in the US, we use the Saffir-Simpson hurricane scale, 1 through 5, but that really waters down what the hazards are for a storm. Even though that scale is only for wind, it really does ignore what the other hazards are from the storms. So we really need to investigate the potential drawbacks of trying to categorize storms using categories based on those local hazards. Next slide, please. Recommendation number 3, you probably saw this in several of the talks as well, is the deploying a multi-pronged approach using artificial intelligence and machine learning, geospatial techniques, and NWP model-based post-processing tools for hazard, vulnerability, risk analysis, and forecasting. Next slide, please. Recommendation number 4 is that really that because we're all in different stages of producing IBF forecasts and using this exposure and vulnerability data, I think that we need to have a kind of an infrastructure in place where we can share lessons from making these types of forecasts and the types of partnerships that we've developed in helping us make these forecasts. So for example, in the United States, we often have to talk to our partners to understand their thresholds for decision making before we know how to actually make an effective impact-based forecast. And so I think sharing those lessons between countries across the globe is incredibly important. And one consideration that we listed here was that maybe this would require a special volume of publication on IBFs in a reviewed journal, maybe once every 2 years or more if that's not really required. And next slide. And lastly, recommendation number 5 is that because this is kind of new territory in the grand scheme of things, we think that we need to enhance capacity building and knowledge sharing through WMO-sponsored workshops and training courses on TC hazards. 2, development of visualization tools for TC hazards and their impacts assessment. And then 3, as we talked about, most of the archives that we currently have for TCs mainly focus on, say, the minimum pressure or the maximum winds of a storm, but they really don't do a good job of archiving the particular hazards that occurred with a storm. So I think we need to think about ways of including the hazard data into those databases to enable a better archive, and then that can go into helping us with research and applications. And before I end, I just want to say real quick that obviously there are lots of workshops that are ongoing across the world in different regions. I know in the United States and in our region, Region 4, we have a yearly 2-week course where we train international meteorologists on tropical cyclone science. But that course really hasn't changed much over the past, say, couple decades. And so with this move towards IBF, looking at vulnerability and risk, really, I think, lends itself to us modernizing these courses and trying to train forecasters in how to communicate forecasts and actually provide in-pace-back forecasting instead of just focusing purely on tropical cyclone science, because there are so many other ways that we can get that information at this point. Okay, next slide, and we'll just turn it over to some questions to be thinking about in your breakout sessions. Go back one more, please. There you go. So impact-based forecasts for TC hazards require knowledge about non-meteorological factors such as engineering, geology, socioeconomic sciences, etc. So the question I think we have for everybody is, how much should the knowledge of those factors rest on the shoulders of meteorologists and hydrologists? I know as a forecaster, I don't know much about how landslides occur. And so asking me to put out an IVF that talks about how the rain may produce landslides and mudslides, for example, I don't have the skills for that. So what is the best way for weather services to efficiently incorporate those factors in real-time IBFs? 2, in spite of significant developments in all aspects of monitoring, there's always going to be uncertainty in the forecast. And so we've gotten better in actually communicating the hazard, but maybe we haven't gotten that great in communicating the uncertainties in those hazards. So how could weather services incorporate those uncertainties in the hazard assessment in the warning bulletins and products that they issue? And then thirdly, which we've touched on multiple times here, is that these hazards don't occur in silos. They occur concurrently. They might occur in different times and in different space. And so in what ways can weather services effectively communicate the impacts from and the protective actions for concurrent hazards when the protective actions that somebody might have to take may be different for each of the hazards? And so if they're occurring simultaneously, how do we effectively communicate to people what they might need to do in these very complex situations? And last slide is just a few acknowledgements. Again, we want to thank our entire working group, the rapporteurs, excellent work on all 4 of these particular topics. We want to thank the WMO, the chairs of the 10th session, Joe and Rob in particular, and then special thanks to Dr. Mohapatra from IMD for his expertise and advice in putting these presentations together. And with that, I'll turn it back over to Monica and Joe.
Thank you, Robbie, and thank you, the entire team.
We are running over time, but we will take some questions given the significance of this one, and we'll invite questions also for BMKG staff as well. So if you have some specific questions from the BMKG talks, we'll also include that. So.
Thank you, Joe. I have 2 questions regarding the impact. So I have 2. In close, yeah, okay. So I have 2 questions regarding the impact part. The first one, so it's almost about the storm surge part. The first question is that so now there's in recent years that few papers talking about the internal variability and the predictability of storm surges related to tropical cyclones.
Dr. Nardo, please.
Yes, so my question is that, in recent years, there's a few papers talking about the internal variability and the predictability of storm surges on the longer term scales. But I know that today the presentation most focused on the synoptic scales. Whether in terms like the IWTC-X can raise a recommendation like we explore the longer term prediction of storm surges as we encourage more research on that. The second question actually is related to the ocean waves. So it's good to.
Thank you for the question. Yes, perhaps considering of the impact of the storm surge, synoptic scale phenomena is the priority. But of course, storm surge information is used for coastal design, creating sea wall and so on. So therefore, such long-term perspective is also important, of course. It's okay?
The second part is about the ocean waves. It's good to see that in the end of your presentation, emphasize that there's still room to do some coupled modeling by combining storm surge and the waves. But for the waves, and as I know that the current wave models, the wind wave models, they predict or they produce significant wave height, which actually is that's average 1/3 of individual waves. So, but it's not the wave height we see on the coast. I think whether when you do the wave forecast, would you provide like the maximum individual height plus the significant wave height? This might because the maximum wave height is more higher risk than the average wave height. I think that's maybe a point worth considering for the next IWTC.
Yes, that is actually a very good point, but I would like to explain a little bit more the phenomena and the process at the coastal places. Of course, ocean wave is very important, and as for evaluating the inundation risk, not wave effect is not merely the significant wave height, but we need to convert the value to wave setup or something, and this is very important. And also, however, sometimes if water level become large, some wave can reach to the beach zone, and or wave overtopping also happened. So such, although the amount of water inundated water is not so much, but of course such effect is very serious and sometimes give damage to the house located in the next to the beach zone and so on. And perhaps such web development inclusion of the web information is of course important. So therefore, the title is actually coastal hazards, not only storm surge. So therefore, in a sense, we should extend the topic not only storm surge but also ocean wave or rather coastal inundation. Okay.
Yes, and small island states, wave impacts are major. We have a question comment online from Bruce Harper that I'll just paraphrase. Bruce, about the terminology used for worst case scenario for storm surge forecast, and perhaps that is not the best term to accurately describe model output. And I'll just ask Andrew to respond to that comment.
Thanks, Joe. Thanks, Joe, and thanks, Bruce, for your question. And the point is well made. And the interesting thing to me is that we've recently been consulting with emergency managers about exactly what terminology we should use to label the higher consequence, lower probability scenarios. And you can get 6 emergency managers in a room, and you will not necessarily get agreement on whether they prefer worst case, high risk, or a purely numerical representation. So we are in ongoing liaison with them to look at when we present. We are certainly, the one resolution we have made is that we will introduce into the product, we will say it's a 1 in 50 chance. So we will put a quantitative estimate, but the interesting thing to me was that the qualitative descriptors to go along with that were very hard to get agreement on.
Just a follow-up question to the earlier one about the storm surge and the prediction of the waves and so on. given the importance of storm surge, for hazards and the large percentage of the deaths associated with storm surge, the presentation for this workshop is on hazards and hazard reduction and improving our service in terms of saving lives. But I'd like to raise the question in terms of the storm surge modeling. Are there sort of scientific unknowns associated with storm surge, or are there sort of extreme technical problems with the numerical modeling of storm surge? Because we're doing probabilities of, we do an ensemble, we take the ensemble, we get 100 tracks, and we sort of run 100 storm surge models, and our probabilities are almost based on the assumption that this is 100 possible versions of the truth. But I think it may be important to at least record or put the question as to whether there actually are any existing scientific unknowns about storm surges, or whether there are any existing sort of modeling problems, in terms of modeling a storm surge.
Thank you. So first of all, I would like to say that, so basically, storm surge model is very simple. And however, it actually predict quite reasonable storm surge values if the forcing is adequately put. So the forcing is, of course, wind and pressure, which is very important. But of course, there are some inconsistency with the real situation, especially in real-time forecast. So I think there are several advanced storm surge models and also very primitive storm surge models. And it is quite interesting that both of models can calculate almost similar values. So there is not so much difference. And considering of the computation resource, simple storm surge model is quite handy and useful for many scenario calculations. So that is why many national services still using simple storm surge model, but there is not so much big room for improvement. So practically, such simple storm surge model can be used for operation purpose. And perhaps, of course, it is related to the previous question. Basically, storm surge model calculate storm surge values or storm tide. Storm tide may be included, but wave effect is generally not included. And wave condition can be calculated from wave model, but comparing with usual storm surge model, wave model requires quite huge resource. It takes longer time, and which is not appropriate for many calculation using ensemble method. So that is the problem, recent problem, and to be modified. It's okay.
So to paraphrase your reply, there are not really any major scientific challenges with storm surge per se, but there are still major scientific challenges with the wave component superimposed.
Yes, wave component and also improvement of input, which means wind, weather condition, wind field, and surface pressure.
And how important is that in terms of our warning services and so on? Are we kind of maybe giving incorrect warnings because we're not incorporating the wave component correctly?
So I think that many national met services actually operate wave models, and based on calculated wave models, so they estimate wave effect, namely wave setup and so on, and add to calculated storm surge and evaluate total water level, considering the risk of coastal inundation and so on.
And we've just got another input from that question as well.
Yes, and I don't want to say that personally, I'm not fully convinced that there's no scientific challenges in storm surge field. I mean, there's several topics, research topics we can go on. One is that the coupled process is not just coupled with waves. It can be coupled with rivers, and it should be coupled with rivers, and also the land process. There's something really challenging for the coastal flooding area. In a big river, actually, I mean, you have to consider the floodings, right? not just from the rainfall. And the second area is the impact of the mean sea level rise. So, and in different seasons and different weeks, and you may have different mean sea level references. But for storm surge modeling, for the ideal circle, it only consider two-dimensional field, so it doesn't include the mean sea level. I think there's few things we still need to work on that.
Yes, I don't know if this is silly questions, but regarding rainfall measurement. So in the first talk, it says most reliable source of observation. So should we worry about the wind? I mean, very high wind during tropical cyclones, and the measurement is done during that high wind. So what's the impact of wind? It's my own worry, actually. I want to know.
So is the question, do we need to consider the impact of high winds on rainfall measurements?
It's ground-based rainfall measurement. Rain gigs, or specifically, turbulence over the rain gigs and the angle of rainfall on that rain gig.
Yeah, I think it's a fair question. I don't know if Alex is online, maybe wants to say anything, but I don't have an answer for you so much as to the reliability of the observations in that situation.
Yeah, my question again, I think there is a very large underestimation, I mean, among these ground-based measurements.
Yes, this is a challenge. Like many times, model estimated rainfall, they are underestimated or overestimated, and there is large displacement also in the center of the area which is predicted by the models with respect to rainfall. So that is a challenge.
Thank you.
Yes, thank you. I have a comment and suggestion for Craig and Alex presentation. So firstly, in 2021, so Vietnam, with the support from UN Escape, we cooperate with the social scientists from UN Escape to develop a platform to integrate the hazard probabilities forecast for information from our ensemble system with the socio-economic data sets to provide the tool for the forecaster to identify the number and also the location of different like factor can be affected by the rain and the wind. So I think those in the books published last year had a lot of information that match your presentation and also the suggestion of a common application for integrate the hazard and also the social economic data sets to identify the potential impact. So I think it's very good if those information can be included in your report. So, and I think it's also the good start for the visualization platform for tropical cyclone hazard and impact. And we are happy to join and also to share and further develop the current tool, which is we already have with support from UN Escape. So the second question for BMKG, because you said in your report that after the survey with the post-event, there is a requirement of integrate the action, that's the proposed action to the public. So what are the plans for BMKG? Because you have the BMKG and also BNPB or BNPP, the disaster risk management. So who will be responsible for that kind of proposed action to the public? Is that included in the warning, or is separate, or is it like have like the separate message from the disaster risk management? Thanks.
Okay. Well, I would like to respond the last things that BMKG on our roadmap and also plan. And you are right that the approach of the early warning is not to be completed also by the informations of the effect and also how it need to be respond. So this is the part that we need to work much in the future because since the Indonesia is also big countries, we need to inline and enlarge the scalability of the, before we move into the service, we will work on the legal aspect because this is the things, if we put the roles in every provider until who need to be respond in every early warning, once it's established, so all organizations will follow up in the future. So we will work step by step and we will have another second step in the next year with delivering the approach of the provincial-based services because as you seen yesterday, you just visit the Bali office, so they will take fully responsible for each province for Bali. So in the future, we also have the 37 different provinces, so they will also take care in every province. So we expect that that early warnings need to be downscale, not just only on the national level, but it's also approaching on the another administration's level. And the other side, we also enlarging the capacity of the on the early warning itself, expanding the time basis, yeah, because as we know that the early or initial state is the main issue in Indonesia, so we're also working hard, proposing with the new skill with the probabilistic forecast. As an NWP approach also, we start to develop, not just only the downscaling approach, but we're working also in enlarging with the ensemble prediction system. And maybe next year we will also start to implement the coupling model. So that's some items that we work on. So there is a technical aspect, but also service delivery aspect. Thank you.
Thank you. And we've that's enough for questions for this session. I will just like to advertise for the breakout. These are the recommendations, so you can use the URL or the QR code to access the documentation, especially for the breakout leaders and note takers, and for those online. We do encourage your input. If you can type your responses via the Jamboard options, we will use that as the basis for assessing the recommendations that will be addressed tomorrow. So just in terms of the time, we do apologize for running. We are running behind time, but I think both the presentations and the discussion are worthwhile. So we are going to have a break now, and we will go to the breakout rooms that will be same listed out in the foyer for your locations. We will have 30 minutes for the break. So if we start our breakout rooms at 11:45, and you'll have until about up to 1 o'clock to have your breakout. Lunch will be from 1 o'clock to 2 o'clock. So in the program, especially for those online, we will be resuming at 2 p.m. for topic 6. So 15 minutes after the advertised time. Appreciate that the lunch is not as long as advertised, but I think that's not too bad. An hour you can have lunch, and if your breakout room is finished before then, of course you can have some extra time. So just once again, a round of applause for all the speakers' presentations from this morning. And we have one announcement from BMKG. Thank you, Diana.
Yeah, thank you, Pak Jo. Attention, please, to all participants. We kindly remind you to please keep your mask on. Please keep your mask on, except when you are eating or you're drinking. And if you need some, you can get it here, or you can ask to another local committee in the registered desk. Thank you, and enjoy your coffee break.
Yes, and if you need PCR or antigen test before you return to your country, you can also contact our local committee. For the PCR test, that's around 275,000 rupiah, and for the antigens, around 150,000 rupiah. So if you need the PCR test or antigen test to go back to your country, please, you can register to BMKG Secretariat. PCR around 275,000 175,000 rupiah, and for the antigen 150,000 rupiah. Thank you very much.
Okay, folks, let's go ahead and get started. This is our final topic and final afternoon of IWTC. So for this topic, we're going to be looking beyond the timescales and the spatial scales that we've been looking at up to now. So specifically beyond the synoptic scale, including subseasonal, seasonal, and climate change variations in TC activity. And so I would like to introduce and express my sincere thanks to our two topic co-chairs, Phil Klotzbach from Colorado State and Marie-Dominique Leroux from Météo France. And they're going to be running this topic session, so I think Phil's going to come up first. Sorry, I should have given you a warning so you're not running.
Good afternoon, everyone. Hope all of you had a fantastic lunch. And so now we're going to be shifting gears from most of what we talked about so far has been up to date about days 5 to 7. So this session is going to be looking at everything from days 8 to 100 years from now. So covering a lot of ground here. I know we have a lot of really cool stuff. I don't want to blabber on very long. So I will turn it over to Frédéric Vittard, who I hope has access to everything that he needs to do his presentation over Zoom.
Hello.
Hello,
Can you hear
Frédéric.
me?
Perfect.
Okay, sorry, I had to do a change at the last minute to my laptop because my desktop didn't seem to work. Okay, sorry, I need a bit of second. So I will share my screen now.
Right now, we do not see your screen, but it may just take a minute.
Okay, let's try again. Sorry. Screen, desktop 1, share. You can see it?
Yes, yes.
Okay, I will put a full screen. I don't know how to get rid of that. And sorry, I have a problem with the video. Okay, I don't know how to put a full screen here. Okay. I have to move the bar. Doesn't want to move. Okay, put it up. And okay, I am in presentation mode.
Yes, that looks good. Thank you.
Okay, I have a problem with the video, which. Okay. Okay, so I will start now. Okay, that's an old one. Okay, so I'm Frédéric Vittard, so I am from ICMWF, and I will give a presentation on the topic 6.1 on subseasonal TC prediction, which so I am a rapporteur with Karl Schweck. So the working group composition includes so myself and Karl, plus Susanna Camargo, Joanne Camp, James Darlow, Russ Ellsbury, John Gottschalk, Kurt Hansen, Justin Jackson, Matthew Janiga, Philip Klotzbach, Xiaoyin Li, and Masao Nakano, Kazuto Takamura, Yue Takaya, Michael Ventris, and Joe Wang. So this talk will have 3 parts. In the first part, I will talk about the modulation of TC activity by subseasonal modes of variability. Then I will talk about simulation of subseasonal TC activity in S2S and sub-X models. And then I will talk about operational subseasonal forecast of tropical cyclones. So this presentation will focus mostly though on changes, on updates over the past over the past 4 years, so since IWTC-9. So the first part is so about the impact of tropical waves on the tropical cyclone activity. There are several well-known sources of subseasonal predictability for tropical cyclone coming from tropical waves. So have been identified since the early 2000s. So they include the Madden-Gilliland oscillation, which which is well known to modulate tropical cyclone activity since the early 2000s. So this affects all tropical cyclone basins, and is recognized as one key source of predictability at the subseasonal timescale for tropical cyclones. Then there is a BSISO, which is a boreal submarine transitional oscillation, which is this northward propagation of the MGO in boreal summer. Then we have equatorial Rossby waves. We have Kelvin waves and also mixed Rossby gravity waves. So over the last few years, there has been quite a number of publications trying to focus more on the impact of the, for example, MGO BSISO on a sub-basin level. While before most papers were looking at the general impact over a whole basin. So the more recent focus has been more on looking at the subseasonal scale, sub-basin scale, sorry. And here is an example of the paper from, this figure is taken from a recent paper by Fowler and Pritchard in 2020, which shows on the left panel, it shows a composite of UA50 and U200 as a function of the phase of the MGO from phase 1 to phase 8. On the right panel shows a composite of the tropical cyclone genesis potential index as a function of the phase of the MGO, so from phase 1 to phase 8. And as well as the decomposition of the GPI, the various components of the GPI, for example, the vorticity, the humidity, potential intensity, and shear, vertical wind shear. So the top panel is for the region of the South China Sea, so the southwest part of the basin, while the bottom panel shows the same diagnostic for the eastern part of the West Pacific. So it shows that over the South China Sea is very sensitive, so to the evolution of the MGO, with a reduction of vertical wind shear preceding an increase of mid-level moisture, while the eastern part of the West Pacific seems to be less sensitive to the modulation by the Madden oscillation, with an increase of moisture preceding here the vertical wind shear. There's been also a series of studies more recently trying to look more at the competitive impacts of various sources of predictability on tropical storms. So we know that ENSO has an impact on tropical storm, MGO has an impact, but how do these sources of predictability interact on tropical cyclone activity? And there have been several papers. So some papers showing, for example, that the preferred phase of tropical cyclone genesis associated to the preferred MGO phase for tropical cyclone activity over a basin can change depending on El Niño or La Niña. Another important scientific research advance, I would say, over the last few years has been quite a lot of studies on the impact of extratropical waves on tropical cyclone activity. So it was actually one recommendation from the last IWTC to pursue research on extratropical tropical interactions. And several recent studies show that the Rossby wave breaking tend to reduce TC activity on subseasonal and longer time scale, so through the modulation of vertical wind shear and tropospheric humidity. And this plot is taken from a recent paper by Wang et al. In 2020, where they show a composite of tropical density function as a function of the intensity of the TUTT, which is a tropical upper tropospheric trough. So when it is strong, top one is when it is strong over the Atlantic, and bottom panel is when it's strong over the Pacific. So we see that when the TUTT is strong over the Atlantic, so the TUTT is a preferred region for Rossby wave breaking, and this saw a window of interaction between the extratropics and the tropics. And the top panel shows that when the TUTT is strong over the Atlantic, so we get a significant reduction of tropical cyclone activity. The bottom panel shows that when it is strong over the Pacific, we get a reduction of tropical cyclone activity over there. However, I mean, some paper indicates that Rossby wave breaking may occasionally be linked to a tropical cyclone formation, and that has been shown in a recent paper by Takimura and Mugakawa 2021, which is not necessarily contradictory with the first statement. So an important question, of course, for the research community is how well do dynamical models reproduce those modes of variability, the source of predictability, their impact on tropical cyclone, and ultimately what is the skill of current state-of-the-art S2S models to predict tropical cyclones. And to be able to perform this type of study, we need a lot of the data set, a large set of model reforecast. And currently, so there is two big databases of subseasonal model reforecast. One is a WIP WCIP S2S database, and the other one is a SubX, which is in real time, while S2S has a 3-week delay, but the SubX is restricted to the North American models. So for the last few years, those models have been generally updated. They are running usually with a finer resolution, like at ICMWF. The subseasonal forecasts are now running at a 18 kilometer and 36 kilometer resolution. And there's been several publications indicating that the skill of those models to predict the MGO has improved compared to previous version a few years ago. Over the last few years, there's been also a few new models which have been available. One is a CSM2 model reforecast also from the GEOS S2S2 and the SPEAR from GFDL. The tropical storm track have been those tropical cyclones have been tracked in some of those databases, like in the S2S database using the same tracker. And those tropical cyclone tracks are now publicly accessible to the research community. And several studies have been done on those tracks. And this is recent results by in a paper by Lee et al. In 2020, where they try to evaluate the skill of the S2S, the model from the S2S database to predict tropical cyclone activity from week 1 to week 4. So here we are looking at a weekly tropical cyclone activity over a weekly period. And to assess the skills, so here they use a Brasty score, which is widely used to evaluate the skill of probabilistic forecast. So the Brasty score is based on so the high value of a Brasty score, the higher the value, the better. And when it is positive, it means that the skill of the model is larger than climatology. And when it's negative, it's worse than climatology. Now, the issue is how do you define climatology? And in this figure, the dotted line represents the skill relative to a climatology computed by taking a fixed climatology of tropical cyclone over the whole season, while the solid line represents the skill when we use a seasonal varying climatology. So the main take-home message from the top panel is that when we use a fixed climatology, some models like ICMWF show some skill to predict tropical storm up to 4 weeks. But when we take the seasonal varying climatology as a reference, the skill is generally doesn't extend more than a week, except for ICMWF, which sometimes over some basins, like the Eastern Pacific or Western Pacific, shows some skill at week 2. However, I mean, the evaluation of this skill was done when without doing any calibration by just scoring the raw data. And in this same paper, I mean, they propose also ways to calibrate. So they explore several ways to calibrate those tropical cyclone subseasonal forecast. And the left panel on the bottom shows actually the grid point map of the Brasty score when we use a fixed climatology with the ICMWF model at week 2. Middle panel when we use a varying climatology, so that's the same message as above, showing the clear reduction of skill. There's a little bit of skill over South Indian Ocean on the East Pacific. And the white one is after calibration of the forecast, showing a clear improvement compared to the uncalibrated forecast. And showing that actually there is some skill at week 2 here over most of the basin, except here over the Atlantic. Okay, so I will go now to the last part of this talk, which is about operational subseasonal forecast of tropical cyclones. And probably one of the main highlight from since the last IWTC has been an increase, a very sharp increase in the number of available operational subseasonal forecasts. While at the IWTC-9 there was just a couple of models of subseasonal forecasts available. There is no many more. So we have operational subseasonal forecast issued by NOAA based on the dynamical model, from ICMWF, from a dynamical model, from Bureau of Meteorology, which is a new one with dynamical models. They have Access S1 model. CSU is issuing S2S forecast using a mixture of statistical dynamical forecast. The dynamical forecasts are used to predict the predictors of this statistical model. And then then we have also US Department of Defense, which issue a 2-week TC formation outlook, US Navy. And then there's also the private sector, which is also issuing forecasts based on a combination of NWP forecast and tropical wave statistical driven forecast. And I expect that at the next IWTC, there will be probably more. So there's currently less models, less operational signal forecasts than there are seasonal forecasts, operational seasonal forecasts. But I think this is catching up. So here's a verification. Here is an example of a few products out of those operational forecasts. The most typical product from dynamical models are sort of a grid point maps showing for each grid point the probability of a tropical cyclone passing within a 300-kilometer radius over a weekly period. So here is an example of a forecast from Bureau of Meteorology. The bottom panel represents the strike probability map for week 2 for forecast which started in April 2021, while the top panel represents the same figure but for week 3 forecast. So on the tracks, we can see here how the verification track for this specific week. So what we can see here is that at week 2, the model predicted relatively well that there will be quite some probability of tropical cyclone strike on the western part of Australia, on the low risk of tropical cyclone strike on the eastern on the eastern side of Australia. For week 3, it's less clear, but there is still a bit more higher probability on the northwest, over the northwest coast, where actually 2 tropical cyclones took place. So I say that's a general product for that dynamical model, but sometimes those dynamical model S2S tropical cyclone forecast can be issued for individual forecasts to predict, for example, the pre-formation or ending stage of a hurricane. And this is here from a recent paper by Helsberry, where this on the right panel, it looks at the prediction of the end stage of Hurricane Linda or the pre-formation stage of that cyclone. So currently, this is a product that goes up to day 14. So it's using the ICMWF medium range forecast, but there are plans to explore the predictability beyond day 14. So forecasts, of course, need to be verified. And this is another verification here from NOAA, where they verified the skill of the 4 models they are using to issue their 2 weeks outlook. One is CFS on the top panel, second is ICMWF, then GFS on the Environment Canada at the bottom, for which that's verification for week 1, 2, and 3. So here the skill score used is a SEDS, SEDS, which is a score that is well adapted for the verification of probabilistic forecast for rare event, for the occurrence of rare event, which is really a problem when verifying subseasonal forecast of tropical cyclones. And what it shows is that there is here three main messages. One of the messages main message is that at week 2, week 3, the models, those 4 models, all display more skill over the East Pacific than over the North Atlantic. That at week 3, although of course there's a degradation of skill week by week, as expected, but even at week 3, there's still some area of substantial skill, particularly over the East Pacific. And of the 4 models, the ICMWF perform quite better than the 3 other models. Okay, so I will conclude now by saying that progress has been made by the scientific community over the last 4 years to better understand the sources of predictability and modulation of TC activity at subsequent time scale. So there's been particularly some significant improvement in better understanding the impact of BSISO, and also to better understand the impact of MGO on BSISO on a sub-basin region. And then there's been also significant improvement in the understanding of the impact of Rossby wave breaking on tropical storm development. There's been a big surge in the number of operational subseasonal forecasts or tropical cyclones over the past year. And the skill assessment suggests that most models have little skill beyond time varying climatology if we score the raw data, but we can improve significantly that skill by post-processing calibration. On my last slide, there's a recommendation from the group, so I don't think I have time to go through it. So I will probably leave the slide as it is, and I will stop here. Thank you very much for your attention.
Well, thank you very much, Frederic. If you can, it'd be great if you could stay on for about another 90 minutes for question and answers. Thanks so much. But I meant to also, when we're switching over, just thank the rapporteurs and the working groups. It's been fantastic working with all of you, as well as Marie Dominique's been great working with you. So now we're going to shift gears and move to a topic that's near and dear to my heart, Colorado State, seasonal tropical cyclone forecasting. This is a topic that, let's see, we got this started about the first official seasonal hurricane forecast that was publicly released was Colorado State back in 1984. So it's about a 40-year-old operationally, and Neville Nichols at the Bureau of Meteorology actually published, best I can know, the first tropical cyclone forecast paper a little bit earlier, even in the early 80s. So this field has come a long way. We have a lot of contributors, and now I will turn it over to Yuhei to get us started. So thanks so much.
Good afternoon, everyone. I'm Yuhei Takaya of Meteorological Research Institute of JMA. First, I'd like to thank my co-rapporteurs, Louis Philippe Caron, and also thanks for the Philip Crosper and Marie-Dominique Lalo. And I would like to acknowledge the many contributors listed here, and I also thank for the WMO for inviting me here. So in this talk, I would like to summarize the seasonal tropical cyclone forecasting, topic 6.2. And this topic features several things, including the services aspect as well as the science aspect, considering the theme of this workshop and the recommendation of the previous IWTC. And the services access aspects includes the multimodal tropical cyclone forecasting and intercomparison and seasonal tropical cyclone landfall prediction and user applications. And we also discuss about the recent development of the machine learning and AI and the seasonal tropical cyclone predictability in ENSO neutral conditions, and also the annual to decadal TC prediction. We also have the updates in this report, but maybe I don't have time to go through the update of the research and operation group. So let's begin with the multimodal tropical cyclone forecasting and intercomparison. The provision of the operational sub-seasonal to seasonal tropical cyclone forecast is one of the operational demands of National Met Services, which is identified at the GDPFS symposium this year, but has not been implemented as the WMO coordinated activity. So we need to do more research, and the research coordination of the multimodal intercomparison of seasonal tropical cyclone prediction has significant benefits, such as creating the transparency which promotes the confidence with users, and encouraging the harmonization and standardization of metrics and lead times and the metrics, and creating an evidence base to promote understanding of the state-of-the-art research and development, so we can know that how the tropical cyclone season prediction is capable. So one of the pioneering initiative is for the tropical Atlantic basin, and the community has the online platform for the multimodal intercomparison, which was started in 2016, and collected data every year for the Atlantic basin hurricane season. And to maximize participation, only basin-wide deterministic metrics are gathered. The products are listed here, which include numbers of named storms, numbers of hurricanes or major hurricanes or accumulated cyclone energy. And this activity relies on the voluntary participation of the various groups, and the nearly 30 groups join this activity, including the groups include the private companies, med services, and universities, as we see many organizations and groups. And this initiative gives the idea of the current skill of the numerical model or the statistical model. And here I'm showing the mean squared error, squared skill for hurricanes and major hurricanes. Basically, the positive value shows the multimodal ensemble forecast overperform the reference focus. Here, the blue is against the climatology forecast, and the red indicates the skill against the 10-year persistence. So for the Atlantic basin, we see some meaningful skill with the multimodal ensemble. But as I said, this is Atlantic basin. So maybe we think that there is an opportunity for expanding for the other basins, such as the Western North Pacific. So let's move on to the tropical cyclone landfall prediction, because if we think about the values for the users, the tropical cyclone landfall forecast is more relevant to the user decisions, and we think we would like to explore the possibility of the tropical cyclone landfall predictions. And here I'm showing the recent studies identified several climate drivers for modulating the interannual variability of the tropical cyclone activity in the Western North Pacific. And these are the ENS types, or the Pacific Meridional Mode. We heard about this yesterday, and tropical North Atlantic and Atlantic Meridional Mode in Indian Ocean. So we see various kinds of the sources of the predictability for the Western North Pacific tropical cyclone activity. Here I'm showing that this figure from the Professor Johnny Chen, and this this figure shows the demonstrations of the regional climate model version 3 forecast for the Western North Pacific cyclone. And the bars show the deviation from observations. And the bars, the different colors show the different coastlines. And they found that the South China, Vietnam, and the Philippines coastlines has a good scale compared with the standard deviation of the climatology. So for some reasons, the researchers found the meaningful scale in terms of the tropical cyclone landfall prediction. This slide for the North Atlantic, and again, these previous studies identified the area we expect to have the skillful skills, and some studies actually demonstrate or investigate the skill for the landfall, tropical cyclone landfall. For example, the ECMWF model or Met Office model or GFDR models. This figure illustrates the seasonal tropical cyclone landfall prediction for the North Atlantic region. This figure from the Murakami et al. 2016 in Journal of Climate, showing that the GFDR model, on the right we see the high floor model, on the left we see the high floor model, on the right we see the floor model. And for example, if we looked at the high floor model, the tropical cyclone, a seasonal tropical cyclone landfall prediction, for the tropical cyclone for the Caribbean coastline here, then the correlation scale for the Caribbean Sea is actually around 0.6. So this is quite good in terms of the seasonal prediction. So this is promising. And for the Indian Ocean, the RMC La Reunion has experienced with the approach using the classification technique in order to better describe the spatial distribution of the tropical cyclone tracks. And they found some drivers. For example, if we have the El Nino conditions, the tropical cyclone tends to approach the Madagascar island, and in La Nina condition, the tropical cyclones tend to approach the Madagascar. And they also found the association with the subtropical Indian Ocean dipole. So based on this finding, they experimentally developed the products for the tropical cyclone classification. So this basically this product shows the likely the tropical cyclone track forecast, season forecast, and we think that this kind of product is more useful than the basin-wide metric. So we also discussed about the application of seasonal tropical cyclones, but currently the operational products are much more basin-wide metric, and which is very much science-driven than the user-driven. So we have to meet the user needs, and if we provide a basin-wide metric or the products, so currently the forecasts are mainly used to raise awareness of the stakeholders. So it's not really useful for the actual decision making. So we would like to improve this situation. So we need to bridge the gap between the science and applications. So as I said, maybe we can explore the capability of the tropical cyclone landfall focus, for example, Caribbean area, coast or South China, Southeast Asia regions. We also discussed about the machine learning technique. And the machine learning can be used for the seasonal tropical cyclone forecasting. For example, the machine learning can be used for the to improve the statistical model, and also machine learning can be used for the predictors mining or patterns extractions. But we also noticed that these pioneering studies show the potentials of the AI and machine learning for the seasonal tropical prediction. But we also noticed that the lack of large amount of training data can hamper their applications. Because if we consider about the seasonal scale, for example, even we have the 100-year climate record, we only just have the 100 samples, so it's very challenging thing to apply the machine learning or the AI technique for the seasonal prediction. But maybe we come up with the better idea. So let's move on to the science part more. And we discussed about the seasonal tropical cyclone predictability in neutral conditions. The current seasonal prediction relies much on the Nth information. But as I said, the previous studies identified the influence of the Indian Ocean on the Pacific Meridional Mode or tropical North Atlantic. So we would like to confirm the influence for the seasonal tropical cyclone. Here I'm showing the figure from our paper, and in this scatter plot show the tropical cyclone density, normalized tropical cyclone density with respect to the Indian Ocean temperature and -3.4 SST. And the colors show the normalized anomalies of the tropical cyclone density, or TC days, if you want. We see a blue color here and red color here. That means actually we found that even in the El Nino neutral condition in this range, we clearly see the influence of the Indian Ocean. And the figures on the right, we see the composite of the anomalies. And again, if we have the El Nino conditions, warm El Nino Nth conditions, we tend to have the more tropical cyclone frequency here. And on the other hand, if we have the warm Indian Ocean and the cool -3.4, then we have the less tropical cyclone frequency here. And also we found that the model and observations indicate the influence, combined influence of the Indian Ocean and ENSO. So this is promising. And the previous studies also suggested that the Pacific Meridional Mode is one of the predictors for this seasonal tropical cyclone in the Western North Pacific. And this figure from the Zhang et al. 2016 in Journal of Climate. And here, basically, we see the regression of SST and the 2-meter winds on the Pacific Meridional Mode in observations in neutral Nth years. So basically, in the positive phase of the Pacific Meridional Mode, we have the warm SST condition here in the here, and that also influence the frequency of the tropical cyclone in the Western North Pacific. So if we have the positive PMM phase, then we tend to have the more tropical cyclone density over this part, south of the Japan. And this influence also confirmed by the recent studies for the case studies for 2018. And these studies also support the PMM influence in the 2018 season. Let's move on to the North Atlantic. The previous study, the Wood et al. Identified the influence of the Indian Ocean dipole for the North Atlantic tropical cyclone activity. In 2019, in September, the North Atlantic had a remarkably high accumulated cyclone energy. And this paper argued that this is because of the influence of the negative Indian Ocean dipole phase. And another study also suggested that the Rossby wave breaking is associated with the North Atlantic tropical cyclone activity, as we heard in the previous topic. And the anticyclonic Rossby wave breaking event increased the vertical wind shear along the downstream of the slope of the mid-latitude high potential vortice streamers, and that induced the suppressed hurricane tropical cyclone activity, as shown here. But I would say we don't know yet how much the extratropical circulation can give the additional predictability to the seasonal tropical cyclone activity in the North Atlantic. For Indian Ocean, as I said, the subtropical Indian Ocean dipole was found to be a potential driver for tropical cyclone in southwest Indian Ocean. But again, its causality and the predictability need further investigation. Lastly, we also touch on the annual to decadal tropical cyclone prediction. And this figure shows the example of the multi-annual predictions. And the latest forecast indicated that the increased likelihood of enhanced tropical cyclone activity during the next 5 years. And the report also these predictabilities is likely comes from the external forcing, I mean the anthropogenic and the natural aerosols, and initialization of ocean state, including the Atlantic regional variability. And the report also gives the more detailed discussion on the origins of the Atlantic regional variability, Atlantic multi-decadal variability, and the implication for multi-annual tropical cyclone forecasts. And our topics also has the updates of the research and development at the operational and research groups. And for the sake of time, I can cover the all. I just leave these things. Maybe if you are interested, we have a very valuable information in the reports. So please look at. Yes. So here I have the tentative recommendations, but we will have the time to discuss about this, so I will skip this. This comes to the end of my talk, and I don't repeat the all things, so I just leave this. Thank you for kind attention.
Thank you very much, Yuhei. That was great. Now we're going to shift gears from seasonal to decadal prediction to what's going to happen 30, 50, 100 years from now. We'll look at what the latest is on tropical cyclones and climate change with Susana Camargo presenting.
Okay, last subtopic of the workshop. So I'm going to talk about tropical cyclones and climate change. My co-rapporteur on this is Hiro Murakami, and I'd like to thank, he did a lot of the work here, and so we would like to thank him, and also thank the topic leads who were fantastic in editing our report. We have a large working group as we are covering a large number of topics. I would like to thank all of them for their contribution. Some of them are here, and some of them, I believe, are online. So thank to all of you. So we, as I said, we are covering a huge number of topics. The first of them is paleotempestology. If you're not familiar with that, it's basically looking at records of storms using sedimented deposits, tree rings, caves, a large number of paleo records. That has been going on for a long time in the US, but that has been what happened in the last 4 years is the large expansions of the records to other parts of the world, in particular the Western Pacific, the Southwest Indian Ocean, and the Caribbean Sea. There was a recent paper showing, using tree-ring records, that the recent tropical cyclone rainfall is exceptional, comparing even with a few hundred years. So giving a perspective of the rainfall due to tropical cyclones compared to past records. Another new evolution in the last few years is that we start to having more high temporal resolution of these records. Instead of looking clunks of 100 years, starting to have annual variability, a few years variability, and so then we can examine multi-decade and longer variability. One of the most interesting papers I saw in that period is by Lizzie Wallace, in which she tried to, using synthetic tracks, reproduce the records of a paleo record, in which there is a paleo decadal variability. So you can see here in black, this is what her reproduced when she reproduced the paleo record, and you see a clear decadal variability. But she used the same method and do that 1,000 times, then that decadal variability is gone. Which raised the questions, if it's some of the records we see decadal variability, are they something real, or it's just randomness of the location? Because these paleo records are very local. So I think that's an important point that will be important to interpret paleo records in the future. Historical and satellite data, we have been talking about that for a while in this workshop, but just reminding everybody why this is important. We're going to talk about tropical cyclone trends. First of all, there are a lot of issues with the tropical cyclone data pre-1970 when we talk about globally. And in the period 1970-1990, there's a lot of change in technology. Your satellites from early 70s are not your satellites from today, so that influenced your tropical cyclone records. So when we look at global trends, that's something that we always have to take into account, and we cannot be naive when we look at, try to explain the trends that you see in the data. So Phil Klotzbar and co-authors did a very nice work recently looking at the global trends in the last 30 years, and what they found was a decrease in the annual number of tropical cyclones globally, as well as decrease in ACE, the accumulated cyclone energy, which is basically the integral variable that has number, intensity, and duration of tropical cyclones. So both ACE and number of tropical cyclones have been decreasing in the last 30 years. On the other hand, we have an increase in the trend of Cat 4 and Cat 5, and also in the number of short-lived storms. Phil is here, can clarify all the questions you have about that. When you look at the HRSAT homogenized records, you also see an increase in the most intense storms. In that case, they look at the global tropical cyclone intensity and see a trend, an increasing trend, and in the proportion on Cat 3.5 compared with the Cat 1.5 storms. In a follow-up study, they tried to analyze why the Cossin study obtained this increase in the proportion. And basically, Jewson and Lewis found that you have a decrease in the Cat 1 to 5 storms, while there's a slight increase of the 3 to 5, so that makes the trend in the proportional of them. A recent study led by Savin Chand looked at 20th century reanalysis data and tracked all the storms in the 20th century reanalysis, and in that data set, we found a declining trend in the global tropical cyclone frequency. And another recent study saw no trend in the global tropical cyclone days. So these are an overall view of some of the findings and the trends in tropical cyclones. And a recent study that was got a lot of attention is by Wang and Toomey, and they had a follow-up study. What they looked at the distance between the location of the lifetime maximum intensity of the storms and to the nearest land point. And what they found was that this distance globally has decreased, and together with that, there was the fraction of the tropical cyclones that are entering coastal regions has increased, and the time that the tropical cyclones spend over for coastal regions have also increased. They also saw in the follow-up study a positive trend in the number of landfalling tropical cyclones and major tropical cyclones in the last 40 years, but there are no trends by basin. All the trends they saw were global. What I think is most important here is that we don't have an explanation for those dynamic explanation. Why would that happen? I think that's what we saw this. They obtained these trends in the data, but I think we need to understand physically why would that happen. Regarding rainfall, I think there was a few interesting studies recently that saw that there is a tropical cyclone rain rate has increased globally, but increased basically in the outer bands of the storms, while there was a decrease in the inner core, and that's how you can see that clearly in this study by Tu et al. that on the top is your all tropical cyclone globally by hemisphere and by basin. And then in the second panel is your trends in the inner core. And you see basically a decrease everywhere and for all categories, while in the outer region, you have an increase in most locations. That's something I think will be a lot of studies to try to understand what that's going on. In the last few years, there are a lot of more studies looking at detection and attribution in tropical cyclones, and in different ways. One of them looking at the trends, for instance, tropical cyclone frequency. So here we have what we have been observing the last few years, an increase in the Atlantic, a decrease in the Western Pacific, and just to highlight something, and for instance, in this case of the paper by Hiro Murakami, he showed that the GFDL model can reproduce those trends, and then he can look at the different forcing, aerosols, CO2, and try to attribute what's causing the different trends in the different regions. Another type of detection attribution event is looking at specific storms. Like in the case here, we have the case of Maria, and then we have the amount of increase in rainfall compared if you use CO2 and no CO2, and also the increased, so here's the historical, and here you have the historical minus pre-industrial and the future minus pre-industrial in terms of rainfall. And you see there's an increase in rainfall rate in this specific storm. So they did about 22 different historical storms, and they can look at each storm, how much in that model could be attributed to CO2. In 2018, Kevin Reed was very bold, and he did attribution of a forecast. So there was a forecast of a storm, and they produced how much, before the storm even made landfall, how much of the rainfall of that storm would be due to climate change. And then they follow up with that was, of course, as it's done, was done while a storm was still being forecast. It was not peer-reviewed, of course, but they did follow up with a peer-reviewed study and showed that how their results that they did as a forecast compared what they actually did when they did more thorough analysis. And so here is like forecasting advance the occurrence of a storm, how much of the rainfall is due to climate change. They followed up with a study that looked at the 2020 season and tried to see how much of that season was the rainfall was attributed to climate change. And you can see that you can have, especially in the high end of the spectrum, an increase of rainfall due to climate change. So until now, we are talking about trends. We are talking about detection and attribution. So this is all present climate. Now let's move towards tropical cyclone projections. And in this aspect, I think we didn't change a lot from what we have been saying in the last 5 years since the IWTC. So we have been saying for a long time that having higher sea level rise, we have more storm surge accompanying the tropical cyclones. The tropical cyclones will probably be more intense. So here we have higher intensity, higher landfall in the future globally, more Cat 4s and 5s. This is a summary, a review paper we did a couple of years ago. What I really think it changed in the last few years are the projections about tropical cyclone frequency, and that's something that was already mentioned in this workshop. Basically, a few years ago, everybody was saying that we are going to have fewer tropical cyclones in the future, and there was basically one study by Kerry Emanuel that was using synthetic storms and was projecting an increase, but was basically ignored. And since then, we started to having some global models also having a projection of an increase in tropical cyclones. Some continue to do the increase, some an increase. So what happened basically in the last 5 years is that we actually have an increase in the uncertainty of the tropical cyclone frequency. And that's something that's a topic that is a lot of attention, people trying to understand. I'm talking more about that. If you now look by basin, most of the signal is similar, that we have more intense storms, higher rain rate, more Cat 4 and Cat 5, but the uncertainty by basin is higher, especially in the tropical cyclone frequency basin by basin. Something that have been done in the last few years too is look at the storm surge projections. In this case, they did both these studies, try to separate what's the effect of the sea level rise and what's the effect of the change in tropical cyclones. Basically have more intense storms, which also contribute to higher sea level. So in this case, the black is your return period based on historical data. When you have the blue line is when you only consider changes in the tropical cyclone characteristics, basically having more intense storms. Now, when you have the red, when you add the sea level rise change projections on top of your tropical cyclone change projections. And this is for specific locations in the US, and this is a case looking at return period of floods and how it depends of the climate model that you're driving your synthetic models, which then drive your storm surge model. So all these will have influence in your projections. How about environmental factors? As we have been hearing, the ENSO-tropical cyclone relationship is a big story in the present climate. So what's going to happen in the future? One of the big things that have been happening in the climate change community, and a lot of discussion about it, is that all climate models, basically, with very few exceptions, since CMIP 5 and CMIP 3, and now CMIP 6, they all have a mean bias in the tropical Pacific. They basically, they all, that's in the historical period. Most of, if not all, tropical climate models, they are having a trend of a warming in the tropical Pacific in the historical period. While in observations, you have the opposite. You have a decrease. So these could have big impacts in your tropical cyclones because that also has impact in your ENSO projections. So most of the models are saying that you're having more, the El Niños are going to be more frequent and stronger in the future. So that will also have influence in how the tropical cyclones will be modulated by that. If you have, instead of a more El Niño-like future, you have a more La Niña-like future, that will have big impacts in your tropical cyclone projections. This is something that I think will be a lot of work going to be done in the future, because we need to understand that. And also, it doesn't matter what you do, if you're doing downscaling, whatever you're doing, looking at the tropical cyclones directly in the high resolution models, if all of them are doing that. So this is impacting all the projections that we are talking about. There are a lot other teleconnections that affect tropical cyclone activity, and for instance, the Tibetan snow and sea air interactions and all that. Then, first of all, we have to understand how they're being simulated in the models and if they're going to change in the models. That's another question. Are these teleconnections going to be the same in the future, or they're going to change? Okay, we have 4 special topics that I'm highlighting here because are things that had a lot of interest in the last few years. One of them, a lot of you have seen that, Jim Carson had a paper that looked at the trends in the translation speed of tropical cyclones and saw a decrease in the tropical cyclones translation speed about 10%. But what happened then is that there were a few papers looking at the statistical analysis and finding issues with the analysis and then saying, trying to see if that was really a robust result or not. That's in the trends. How about the models? Here's a case of one model. Of course, we have, different models do different things. In this case, this model has no trends in the present regarding translation speed, but does have a slowdown in the future. So I think we have a lot to understand, first, why this slowdown is happening, if it's happening, and what's going to happen in the future, and trying to understand the dynamics for that. This was discussed a little bit in the a previous topic, talking about tropical cyclone frequency. And as I mentioned, there's this big uncertainty change regarding the projections of tropical cyclone frequency. What happened in the last few years, trying to understand that, people trying to use tropical cyclone seeds. So the group at Princeton came up with a different way of thinking about this problem, and they use probabilities of going from a convective cluster towards tropical cyclone seeds, and that's what you usually use, your Genesis index, your probability of having a tropical cyclone. So you have large-scale environment, both for going from convective clusters to tropical seeds and towards a tropical cyclone genesis. So when they use that in climate models, they could explain why some models are projecting an increase in the future and why some models are projecting a decrease in the future, because it's this combination of what, in some models you have more seeds, some models you have fewer seeds, so it depends what's winning, the seeds or the environment that we're going to have this combination explained. So this is really explaining what happened in climate models. And that's confirmed by some other papers that said that they also has this correlation about the tropical cyclone seeds and the projected change. But now we're all talking in model world, so we have then what the other models do. So this argument can be, sounds perfect, but then we, of course, then have the other side. And the other side is, for instance, this Cristina Patricola has 2 papers. One actually was published last 2 weeks ago, a new paper that what she basically did, she blocked the easterly waves coming to the Atlantic. And you would expect if you have fewer easterly waves, it would be harder to have tropical cyclones in the Atlantic, and that's what not happened. So what happened then, you have the tropical cyclones forming in different locations using different types of seeds. So that's in against the argument that the tropical cyclone seeds is going to explain your future projections. Similarly, Kerry Emanuel recently wrote a paper trying to discuss this issue of this probability of the seeds. And his argument is that in his downscaling model, he used random seeding. So if you have random seeding, it's very hard to explain that seeding has an important role in the future. And using his random seeding model, he is able to reproduce interannual variability and climatological tropical cyclone numbers. So I would say that we have two sides here trying to understand what's the importance of the seeds. Are seeds really important? And first of all, what are the seeds? We don't have a good definition for this tropical cyclone seed. So I expect to see a lot of work on that in the next few years. Another topic that I have been very involved on is looking at tropical cyclone risk. As probably all of you know, the reinsurance companies have been having CAT models for many years, and they basically use statistical models. And then in the last few years or so, many academic institutions start to develop their own tropical cyclone synthetic models, risk models. Kerry Emanuels at MIT was the pioneer. We have our own at Columbia. We call it CHAS. And then here is another one by Nadia Blumenthal, STORM. All these different academic models, they have the same ideas of the CAT models from the private companies, with the difference that we want, first of all, to be able to handle climate change, which the private companies, usually they are purely statistical models and they don't handle climate change. And secondly, we use a combination of statistical and dynamical models. Different approaches have more statistics or more dynamics, depending on which university you're talking about. And then we are now able to look at tropical cyclone risk in the present and in the future using that. For instance, our model is open source, anybody can run it. So that's part of the idea of doing that in the academic world. And we started with wind. Most of the models start wind, and then we add precipitation, storm surge, and everything so that we can look at increased risk in the present and in the future. Now we have studies that we went all the way to the economic impacts using these academic models, and also comparing the different academic models and see the impact of using different models in the socioeconomic impacts. So I think that will be very useful for disaster risk management. The reinsurance companies, the private companies are very interested in that, which is wonderful. They're actually now interested in climate change. They were not in the past. And we have been collaborating with the private industry using these models, and has been a wonderful learning curve. So I expect that will continue in the future. And our last special topic is Medicanes, which was already mentioned previously, and is there Mediterranean tropical cyclone-like storms. They have hybrid and shallow warm core with extratropical characteristics, and part of what Kim Wood was talking about, how to classify them, how they fit within the whole spectrum of the cyclones. But in terms of future projections, the studies that exist, which are not many, project a decrease in the frequency but increase in the intensity of these storms, also increase the rainfall associated with the Medicanes, and showing that changes in the SSE and stability will be important for future change. One of the main issues remaining with Medicanes is that there is no data set, there's no IB tracks for Medicanes, so it's really important to develop that, develop a definition, so we go back to the previous topic, how we define all these storms, and also there has been less attention in these storms than other types of storms. And recommendations will be discussed further. And I think I went through all of this. The role of tropical cyclone seeds, biases in tropical models, especially the mean Pacific bias, how that influences tropical cyclones. Inconsistency between some trends and what the models are doing, and event attribution. So far, all that has been done is in terms of precipitation and intensity. Can we do something else? Thank you.
Well, thanks so much, Susanna. I think you did a great job covering quite an extensive area of research these days. So now we're just going to briefly highlight, let's see. Yes. Yeah, we're just going to go very briefly through what we've just talked about, and then we'll obviously open up for questions. So first we talked about subseasonal tropical cyclone prediction. One of the big topics was the impact of extratropical waves on tropical cyclone activity. Certainly I can speak to that from especially August of 2022. I don't think anyone thought at the 1st of August that the Atlantic would have no named storms in August during a La Nina year with a warm tropical Atlantic. But those extratropical waves came in and we had very vigorous Rossby wave breaking, a lot of shear, a lot of dry air, and a month with no tropical cyclones. So one of the big questions is how much predictability do those have? There's tantalizing signals, but most of those come from the tropics. So if you look at the predictions that are out there using wave breaking in the Atlantic, they often focus on ENSO because El Nino normally has more wave breaking. So last year, or this year, we had La Nina and tons of wave breaking. So definitely challenges there. Subseasonal to seasonal skill. There is skill week 1, especially with some of the kind of post-processing. You can get it out to week 2 for certain basins. I thought it was interesting too, highlighting how the Eastern North Pacific had higher levels of skill than the Atlantic, perhaps because Eastern North Pacific storms tend to form in kind of a tight box, whereas the Atlantic, obviously we see storms forming all over the place. The operational subseasonal TC forecast space has increased quite a bit. NOAA does them, ECMWF, Bureau of Meteorology, our group at Colorado State, and also besides a couple other US groups, there are a lot of private sector forecasts starting to do this. I think one thing that would be nice is to kind of, a lot of those are unfortunately kind of proprietary or behind a paywall, so it'd be nice to kind of see what they're using as well, which we found when we did the seasonal forecast stuff from the website that Yuhei showed earlier that myself and Louis Philippe kind of got started. The seasonal forecasts are they're a lot more forthcoming with those, I think, than the subseasonal forecasts. One of the cool things about subseasonal forecasts compared with seasonal forecasts is we can obviously really get down to spatial and looking and seeing like which area is likely to be a target. So here's a couple of examples, one highlighting kind of in a broad area, and then also for looking for systems even before they form for individual storms. Then we moved on to seasonal forecasting. Obviously seasonal forecasting, again, historically has been basin-wide. And there have been some shifts in that. One of the highlights that Yuhei showed earlier was seasonal forecasting for the Western North Pacific, where they're actually forecasting for specific regions. And in there, they found that certain regions were more predictable than others, and I think we certainly find the same. Yuhei also showed in the Atlantic. There's a little bit of skill for the US, but a lot higher skill for the Caribbean. And that's from a dynamical model. I can also say from a statistical prediction model that you actually get more skill for the Caribbean as well. That region seems to be highly predictable, and obviously storms in the Caribbean have huge financial impacts, huge impacts to life and property. So certainly that's if you're going to have skill in a region, that's an area you like to have skill in, as opposed to out in the middle of nowhere where you're not really impacting anything other than ship traffic. Then we also have a lot of applications of machine learning. Machine learning has been tried to be used in seasonal forecasting. I think it's been a bit slow, and I think one of the reasons is because seasonal forecasting, depending on the basin, you've got 30, 50 maybe-ish years that you actually have reliable tropical cyclone data. Obviously, as we go back in time, the tropical cyclone data gets dodgier. Also, the reanalysis gets dodgier, especially prior to the late 1970s. If you're trying to use upper-level wind predictors, things like that, you're kind of stuck with surface predictors. when you go back prior to about the late 1970s, just because we didn't measure upper level winds in a great way. Obviously, another big focus is on trying to forecast hurricane seasons when you have ENSO neutral conditions. Well, it seems like we've been in La Nina forever. We do have ENSO neutral from time to time, and so a lot of different drivers are there from basin to basin. This is just kind of one looking at the Southwest Indian Ocean using the subtropical Indian Ocean dipole. And then I think finally, on this topic, is the annual to decadal prediction. So you have seasonal forecasts that are for 1 year, but especially in the Atlantic, we have climate drivers that tend to go on longer term timescales, longer memory. So we have this Atlantic meridional variability. Others have heard about this Atlantic multi-decadal oscillation, tends to be related to North Atlantic sea surface temperatures. The Atlantic especially been really busy since about 95, when the Atlantic kind of flipped into this new busy period. So you have this kind of skill, a lot of it comes from the subpolar gyre region, where you can actually predict 5 to even 10 years into the future. So I think that's kind of a nice kind of pivot away from the subseasonal to seasonal to shifting over to the tropical cyclones and climate change, which I'll now turn it over to Marie Dominique, who will summarize that, and then we'll discuss the recommendations.
Thank you, Phil. All right, so I will now try to highlight some key results from subtopic 6.3, tropical cyclones and climate change. And I want to thank Susanna and Hero for their hard work and their very nice report that I invite you to read. So starting from the past, the global TC records are reliable since 1990. So we have this 30-year time frame window to extract trends from that we are quite confident in. So the trends are a decreasing number of tropical cyclones and a decreasing accumulated cyclone energy, as well as an increasing trend in the number of category 4 to 5 TCs. And it was also found that the number of short-lived storms has increased. Now, if we look at HERSAT homogenized records, then you have this 40-year time frame window that confirms that there is an increase in the global TC intensity, as well as an increase in the proportion of Cat 3 to 5 storms relative to Cat 1 to 5 storms. And another study found no trend in the global number of TC days. As for detection and attribution, well, the TC frequency trend is basin dependent, as shown in on the top left figure. And what we see is indeed a decrease in the number of TCs in the South Indian Ocean, except for the Mozambique Channel in between Southeast Africa and Madagascar, as well as a decrease in the Western North Pacific. But there was an observed increase in the North Atlantic and the Central Pacific. Then for attribution, studies have looked at specific storms and whole TC seasons, and the enhanced rainfall has been attributed to anthropogenic forcings. Now looking at projections in the future, here at for a 2-degree global warming level. So Susanna insisted on that. There is not really a consensus yet on the projected TC frequency trend, but most studies have shown that the number of TCs annually will decrease, although some studies predict an increase in the number of TCs. And this might slightly vary, but what varies most across basins is the uncertainty on the TC frequency trend. But we have more confidence in saying that the number of Cat 4 to 5 storms will increase in the future, their proportion will increase, as well as the TC intensity and rain rate. So basically for a 2-degree global warming, what has been shown is an increase about like 14%, 15% of the rain rate globally. So it's about, it follows about the Clausius-Clapeyron relationship, but it's more complicated than that, of course. So since there was difficulties to understand the evolution and the trend of TC frequency, over the past few years, the TC seeds have been introduced and discussed. So TC seeds for low pressure disturbances or precursors of TCs, but there is still no consensus and an argument on the effect of seeds on the evolution of TC frequency. So this is an area of studies that we will highlight in the recommendations. About the TC risk, well, since there is quite a lot of confidence in saying that the TC intensity will increase, as well as the rainfall and wind speeds, the sea level will rise and there will be an increased duration of TC landfall. So most likely there will be an increased TC hazard and risk. And in that sense, the TC hazard and risk maps are extremely useful for disaster risk management. So here is an example of the projected changes in the return period of Cat 3 storms. And it shows that large parts of the world faces an increase in wind hazards under climate change, particularly for these severe TCs. So I will now list the recommendations for each of our subtopics. So starting with subseasonal, the research community should expand verification studies of TC predictions from single models towards multimodal ensembles. And there is also a need for consistent verification metrics and comprehensive measures of skill. Then the research community should actively explore tropical-extratropical interactions, as well as TC size and structure predictability to improve subseasonal TC predictions. And third one, operational community should expand their exchanges of model forecast TC formation and subsequent tracks. Looking at the seasonal timescale, the research community is encouraged to develop new skillful and reliable seasonal forecast projects beyond traditional basin-wide metrics that would be closer to stakeholders' interests. So basically, fit-to-purpose projects. Research community is then encouraged to develop a coordinated demonstration project of seasonal TC forecasts based on multiple dynamical systems. The platform should help intercomparison and evaluation with standardized metrics to identify best practices and consider the feasibility of a WMO coordination of seasonal TC forecasts. Regarding the climate change timeframe, the research community should continue to investigate the physical mechanisms behind the number of global TCs using both observations and modeling studies to clarify the expected changes of TC frequency in the future. So here we're talking about TC seeds. And then the research community is encouraged to provide more information on future changes in TC activity at regional scales rather than at a global or basin scale. And finally, the research community should continue to develop and maintain climate data sets related to TCs and medicanes and better quantify uncertainty in these data sets. So before I finish, I would like to thank again all the working group members and our rapporteurs for the excellent work, as well as Phil. It was great working with you all. Thank you.
Thanks, Marie-Dominique. So we have some time for some questions. I don't know, might be best to have Phil and the rapporteurs come up.
Yeah, if Yuhi and Susanna can come up, would be great. Thank you.
Thank you. Roger. Oh, yeah. There's one coming.
I have a question of, I have a question of detail to Susanna and a more general comment. The question of detail is you're talking about these tropical cyclone seeds as regions of close disturbance. Are these regions of close disturbance in the co-rotating, co-moving frame, or are they in an Earth relative frame? Because that will make a huge difference.
So as I said, one of the problems with all these tropical cyclone seed studies is that each group is defining them differently. So we would have to see what each group is doing, and that's one of, I think, the problems with all these tropical cyclones is there is no clear definition according to all the groups. So we would have to go paper by paper and look at what you're saying. So I think basically some of them use easterly waves, and some of them use very small clusters. So we have all the range of different things that you're talking about. So that's a problem. So you're talking about the definition of what the seeds are, and I think that's a very relevant problem. And I think we would have to go to the different groups and try to understand how they're doing that.
Just a quick, more general comment. If you're going to try and understand these changes, you're going to have to understand how tropical cyclones work. And you're going to have a conceptual model. And perhaps it's not a good time to ask you, what is your conceptual model?
Is that a test? I'm sorry.
Okay, yes, another question.
Yeah, thank you very much for the presentation from Madagascar. I really appreciate all the efforts done especially in seasonal forecasting. Because in the Indian Ocean, we are working closely with La Réunion at MSA. We have started like seasonal forecasting for 13 years old now, so little young compared to 40 years, but we're really happy on the efforts, especially thanks to RSMC, La Réunion, starting to forecast tropical cyclone landfall risk, because the indexes that we use objectively, like accumulated cyclone energy, is really not sufficient. For example, last year, 2022, for SAE, accumulated cyclone energy for 2022 in the Indian Ocean basin was just slightly above normal. However, for Madagascar, there was 6 tropical cyclones. It never happened before 60 years. And it do not reflect at all sometimes. It may be inducing error to users, considering only the general indexes. So maybe a suggestion, is it possible to have some impact-based indicator? Or we are trying on that because I think it's closely related with subseasonal forecasting in the topic, first topic, because particularly last season for us, within 7 weeks, we had 5 tropical cyclones. That never happened, 5. And within 18 days, 2 intense tropical cyclones in same region. So considering the timing within the season matters, and also specific privileged area really matters. So we really would like to encourage that and strengthen that in the recommendation. Thank you very much.
Yeah, I agree. I think that's a good idea. I mean, I think it depends a lot on which basin you're in. I think that's one of the reasons why there's kind of a nice, kind of a seamless sweep from sub-seasonal to seasonal, because I'm not sure. I admittedly don't spend a ton of time looking at the 2 or 3 week ensemble forecast for the South Indian Ocean, but sometimes you get pretty good signals, so you might even have seen that. I'm not sure if that was in the models or not, that there was going to be a signal there. When it comes to seasonal predictions, what you find, speaking more from the Atlantic, is if you have a busier season in general, we'll have more landfalls, more impacts. Doesn't work every year. We also, I think there is ways of trying to forecast, not necessarily like X number of storms are going to make landfall, but if you can forecast this accumulated cyclone energy over a smaller region, that I think has higher levels of predictability. So I think to me, it's kind of like, it's kind of like trying to find like a perfect middle ground where like seasonal forecast can actually predict it, but yet also is more relevant than just saying, hey, it's going to be, an average season, because for example, the Atlantic 2 was pretty much a dead-on average season, and we had one, $75 billion hurricane, so it wasn't average from in terms of an impacts perspective.
I could add that there was a very recent project that was built by Météo France that was shown in his presentation for the Southwest Indian Ocean. It's getting towards an impact-based forecast because it looks at the seasonal predictors such as South Indian Ocean dipole, and then it says which areas will be more at risk, and La Nina, El Nino, and so it's a classifying procedure. So you might hear about it again.
I like seeing the thumbs up. So there's a question online. I believe Chris Fogarty had a question in the chat, and then Jack Bevan raised his hand. So what's Chris's question? Can you read that, Munhiko, please? He needs a microphone. What? Yeah, well, right, but if Chris's question that he typed first. You see that in the chat? Yeah.
It's a comment. Interesting that rainfall trend increasing in a more pronounced manner in the outer bands. That's consistent with the increased temperature and the humidity of the environment, which has been in turn known to govern TC size.
Sounds right to me. Because I don't see a question, there was a comment.
Okay, so Jack, you also had your hand raised. Do you want to go ahead and unmute yourself?
Yeah. Question for Phil. It's a little bit of a sidebar, but you alluded to some of the twists of the Atlantic 2022 season. And I think some of the other basins had some twists. The Huangatunga eruption back in January, has there been any work done on the changes in the circulation patterns it caused during 2022 that may or may not have influenced the various tropical cyclone seasons?
Not to my knowledge, but to be fair, if people were doing it, it probably hasn't been published yet. At least I haven't seen anything. So I've been asked that question quite a bit, and it's one of those things where it's like, the global models, I assume, would have assimilated that increase in stratospheric water vapor, and the dynamical models were also very, very bullish for an above average, really, really busy hurricane season. I think ECMWF at one point had 2.5 times ACE normal or something. It was really, really high. But again, it is stratospheric water vapor, so I'm not sure how great the assimilation of that is, but I haven't seen anything yet to say that played a major role, but obviously I haven't done that work myself, so potentially that could have been a factor. Because yeah, I certainly don't claim to have all the answers for what the heck happened this year yet.
Well, the other thing, this is more of a comment, there's continuous African dust. It just seemed to never stop coming this year, and I don't have I'm not enough of a specialist in what generates that to know what would create that continuous plume that was still coming off in September, October, and even November. And that might be another factor. But what I did want to ask about that, given how the 2022 season was a little non-standard in the Atlantic, the way it worked out. So
yeah, certainly. I mean, obviously, Jack, you know that better than me. But yeah, I mean, it was extremely unusual to have a dead August, a very quiet October, and a really robust and busy September. Usually if September's busy, either August or October or both will also be busy. But yeah, there was definitely a lot of dry air, some of it likely coming from, obviously from Africa, and then also a fair amount of dry air coming from the mid-latitudes with all that wave breaking. But yeah, we're actually working on at least August specifically, myself and Kim and others likely as well, to try to kind of hopefully quantify what percentage is which. So I'm not just doing this like I'm doing right now, waving my hands.
Okay,
thank
any
you.
questions? Yeah, Julian.
Yeah, I've got a question for Susanna. You showed that observing technologies have improved vastly between 1970 and 1990, and then said that since then you've had a fairly consistent data set. I mean, is it not the case that observing technologies have continued to improve in the last 30 years, particularly in our analysis of the inner core of tropical cyclones, and particularly those that might increase to high intensities and then weaken very rapidly. And if that's the case, then is it not possible that the observed increase in the frequency of Cat 4s and 5s, which you showed, that might have some bearing on it, the continual increase in observing technologies that we've seen in the last 30 years?
I'm not the most expert in technologies of tropical cyclone. I believe in this room there are 100 more that know more than me. I'll pass to Phil, who has done 90 his trend analysis.
Yeah, I mean, if we're never going to be able to say, hopefully we never have a static observational platform, and with time, the satellites are going to get better, higher resolution, and generally you're going to see with improvements that storms look stronger than they used to just because you have better data. But if you're ever going to use observations to look at climate change, you've got to kind of pick a period, and certainly not saying 1990, thank God we don't have 1990 now. We have way, way, way better technology, but it was kind of a trade-off between can you actually look at anything and having a long enough data set to actually make some analysis. But certainly in the paper, and having studied under Bill Gray for a long time, obviously the technology isn't the same as it was in 1990, but it seemed like at least a reasonable start to kind of get at some of these trends. We basically found like the Cat 4-5 numbers were very slightly increasing up, but more, basically you saw an increase in the percentage, but really what I thought was more interesting is that the global number of hurricane strength tropical cyclones has gone through the floor, mostly in the Pacific due to what Susanna was talking about earlier about this trend towards La Nina. And when we look at those projections in the future, they're all showing basically what looks exactly like a projection you would expect with more and more El Niños. And so since the real world says we're trending towards a more La Nina dominant environment, that's something we really got to get our hand on if we're going to make these projections into the future.
Okay, time for a couple more questions. John, Benjamin, and Sebastian, and that's it.
Yeah, interestingly, I had my hand up for a long time, and then Julian got in and asked exactly the same question, but that I had in mind. But to me, it's important enough. I'll sort of paraphrase it. In this terrific session, you have all these astounding advances on the 3 time scales and so on. To me, that was the greatest surprise. From the talks, I got this impression that we, as the group of scientists, have a belief that there's no longer a problem in the specification of the trends that we can consider reliable since 1990. And as I said, that was a great surprise to me, and I would challenge that. I understand Phil's reply that to do work, we can't sort of wait 100 years. We have to take the data we've got now, and we thought this was good enough for studies, but I think it's putting forward a false message and maybe losing the important message that consistent data, sufficient to do trends is something we have to really think about in the future. So it's no longer a question. My question had been, is this true? Do we really believe that we've got intensity trends and number trends and everything, we've got a reliable data set, or do we believe we have a problem into the future still?
What is the alternative? These are the observations we have. And if we want to look at trends, that's what we have. So we can try to do other things like looking at reanalysis, do a downscaling of reanalysis, looking at models.
Well,
the observations themselves, that's what we have. We don't, you can do paleo and try to, reconstruct long term, but there are all these times with paleo. So I think in some ways, the community is trying to do what they can with the data that exists. Is perfect? Not, of course not. But I don't know what else can we do. Try to define the uncertainties, probably better. That's something.
For example, we could use this as a reason to, or a justification for trying to get, in situ observations in all basins into the future.
That will help the future, not the past.
But the future is, 20 years' time, people are going to be working with the last 20 years' data to, sort of it's only 5 workshops away. We should be helping the scientists of 20 years' time.
I'm all for having more data.
Sounds like a good discussion to continue in the coffee break, but we do have 2 more questions. So Benjamin and then Sebastian. So Benjamin, do you have a mic? Okay, let's do Sebastian first since he has a microphone. Yep, go ahead.
Thank you. I have a question for the subseasonal side. And it's for Frédéric.
Yes.
At Météo France, we are involved in a subseasonal project that is aimed to design end-user subseasonal product regards TC freight. And in this framework, we are conducting monthly seasonal briefing in order to improve our understanding in all the tropical wave involved, especially over the southern Indian Ocean. And during this briefing, since 3 years, we are having a lot of time, a hard time to describe the current state of the Madden and Julian oscillation, despite all the various index that is already exist. So my question is there a way to improve this current index? I think of the RMM index, especially. Is there a way to improve this kind of product to better handle the current status of the MGO that is not so canonical as it could be most in frequent times?
Yes, that's an excellent question. It's true that if we look at the basin like the Southern Indian Ocean, we may need something a bit more precise than the IMMs. The IMMs index is very popular, but it has its limitations. It's known, there's been other index developed, like the RUMI, which is like the IMM, but only for the OLR. There are also some method by Shui Chen from Miami Naval School, which is thought to track, to do some track of MGO episodes. But yeah, I don't have a clear answer to your question now. But people are quite looking at it. I mean, there's different indices for, as I say, for MGO. Each of them has its own strengths and weakness. But there is no consensus yet of a sort of a better index to the IMM to give probably a better for better communications with the users in terms of tropical cyclone formation. So actually, that could be quite a recommendation actually from this IWTC to pursue more research in that area.
Okay, thanks. Sorry, I missed someone else that had their hand up. Who else had their hand? Yeah, do you have a microphone? And then we'll do Benjamin. I promise we'll get to you, Benjamin. Okay.
Okay, I have a question to Sudana. Maybe it's more like comment. So, Bob, this long-term trend in TC metrics, whether it's ocean basin-wide or it's global trend, it's good to see that in the very end of your presentation, you emphasize that we need to understand the details at regional scales, but also want to raise the point that we probably in the research community, we need to put emphasis on the seasonality change. And for example, in the Northwest Pacific, the most significant and the largest trend in the forward migration of typhoons, we found actually it's from the seasonality change, because you got a relatively more TC in the summer and relatively fewer TC in the autumn, winter. So when you're looking at the annual average of location of TCs and also other same for other TC metrics, you have this kind of trend. But there's the trend, it definitely can very hard to explain by the large scale and the annual average climate signals. So we have paper published last year, but I think it's going to be the same problem for other TC trend, like the TC translation speed and intensity. So we need to put more attention on the seasonal cycle change, and also the shift of the spatial shift of the track. For example, if the TC is shifting from a lower latitude to higher latitude, you will expect to have a higher translation speed. So I think we need to more rigorous analysis and understanding on this large-scale trend. And also this probably is a fundamental piece of work before we jumping into the projection. I mean, basing on projection. So we have to evaluate the model performance for this regional performance and the seasonal performance on this TC the variables. Yeah, that's my point.
Absolutely, we have to look at all type of characteristics. But the more you chop the data, looking at, part of the seasons, then if you're having problems looking at trends in the whole season, now you're looking at early season, late season, so the data issue will become bigger. So I'm absolutely agree with you, but I don't think we can stop doing projections and wait to understand everything that's going to the data. Both things are going to be going hand in hand. And there are a lot of things that maybe the trends we have are not real trends. They're something to do with the data and that we'll never have in the model. So that could be. There's no way to know yet. Maybe in 20 years we'll know. But I think part of my way of thinking is like we have to understand the dynamics and try to do idealized modeling and try to understand what could lead to those trends, not only based in statistics, but go beyond that. That's my way of thinking.
Okay, thanks. We'll wrap it up with Benjamin. Last question.
Yes. In a warmer planet, we would expect changes in precipitation, and for instance, also in salinity and stratification in the ocean. And as well, the warming of the ocean shouldn't be expected to only affect the sea surface, can extend to deeper layers. So a deeper, warmer layer and more stratified ocean would have an effect on SSTs. And I wonder whether somebody is having a look if this is the reason for the bias in SSTs in the climate models.
I think people have been looking at a lot of issues in the climate model trying to explain these biases. And I don't think people have agreed in the reason for this bias. The people at Lamont, Richard Seeger and Mark Kane have proposed why the models are doing that. Not everybody in the community is in agreement. So I think that's an open question. Why? Could be salinity. That's another one that we know how much data that we have from salinity from 30 years, 40 years across the world that we can rely on that data. So I'm not saying it's not, but it's hard to say yes or no with the amount of data that exists there, I think.
Okay, well, let's thank our speakers for an excellent session. Thanks. All right, so now it is about 5 till 4. We are a little behind, my apologies, but a lot of really good questions there. Let's go ahead. So here is the list of proposed recommendations that I believe were distilled by Phil and Marie-Dominique. This is also the tiny URL, so you can access those for our breakout leaders and note takers. And that information is going to be on the board out there again. Let's see, can we do around 4:15 or so? Can we start heading over? We have a break now. Head over to the breakout sessions at about 4:15. That'll give us about an hour and 15 minutes at least. Take us to 5:30 or so. If you need longer, feel free to take it. But can we at least be in the breakout sessions till about 5:30? And that'll wrap us up for the day. Did you have anything, Joe, you want to say? Yep. And I also want to thank our online participants. And if you have any contributions you'd like to make online, for example, to the Jamboards, if you could complete that by 09 UTC, which is, I don't know the time, is that an hour from now? So I can't do the calculation off the top of my head. 5 o'clock local time, 09 UTC. Anyway, so thanks again. Go enjoy your break, coffee and so forth, and we'll see you in the breakout sessions.